Welcome to the Cyanotype primer by Free World Blues. And the word blue is apropos here because the cyanotype process is a photographic method that makes use of photoreduction of iron 3 ions or salts with carboxylic acids to produce Prussian blue, which is a mixed oxidation state cyanide complex. Specifically, it contains both ferrous or iron 2 and ferric or iron 3 ions. And in fact, it is this pigment Prussian blue which gives its name to cyanide. Many cyanide complexes are cyan-colored or blue-colored. And when working with cyanide, I strongly recommend that you dress in blue such that any stains upon your clothing are less visible and less likely to ruin your wardrobe. As you can see, I am appropriately dressed here. It's of course a fashion faux pas to wear a blue suit over a blue shirt with a blue tie, but please indulge me, this is chemistry after all. Now, none of the compounds or processes demonstrated in this recording are especially hazardous, as both the precursor potassium ferrocyanide and the resulting Prussian blue bind the cyanide ion quite tightly, and this reduces their toxicity as cyanide must first enter solution and find its way to your cytochrome C oxidase in your mitochondria to exert toxic effects. However, in chemistry, as in all facets of life, it is your responsibility to ensure your own safety and the safety of those around you, and all you choose to do, you do at your own risk and on your own recognizance. The cyanotype process is typically used to create pictograms, which are recordings of shadows of objects, often flora, but can also be used to create positives from negatives, as it is itself an inherently negative printing method. It can also be used in camera, which I will demonstrate later in this recording. Now, I will be diving deep into the chemistry in this recording. In fact, it's my aspiration that this recording will be, at the time of its publication, the single most detailed resource on the cyanotype process in existence. It is, of course, up to you to adjudicate my success or failure. So be forewarned, we're going to be talking about ligands, we'll be talking about oxidation states, we're going to be talking about coordination spheres. Do you find that amusing? Do you find it amusing that we're going to be talking about stoichiometry? Yes, we're also going to be talking about pH and pKa for polyprotic acids. We'll be talking about photoreduction, energy levels, electron spin, and we will definitely spend a lot of time talking about atomic orbitals. That said, I will quickly prepare the cyanotype sensitizer and demonstrate the process in this introduction before going through each step in detail. A glimpse of the goal can focus the mind, the sight of a peak can motivate, I think, the climber. So let's begin there. The first reagent we will use is ammonium oxalate, shown here. I've chosen not to show the synthesis of this compound in the introduction, really for 4 reasons. First, I already have quite a mass of this compound, ammonium oxalate, prepared. Second, this reaction isn't particularly interesting. Third, it's a meaningfully exothermic reaction. It's actually the only step in the cyanotype process which is strongly exothermic at lab scale, and hence it's not something I can do, quickly. I need to run the reaction gradually to prevent it from overheating. And fourth, this reaction involves ammonia solution, also called ammonium hydroxide. And the issue with aqueous ammonia is that it is constantly changing concentration, so it's difficult to pre-measure the correct amount and then just run the reaction quickly. This ammonia is ostensibly 25% on a mass by volume basis, but the problem with ammonium solutions is that they're constantly off-gassing to the atmosphere, and so the concentration tends to decrease over time. And of course, the manufacturers know this, so it's common for chemical producers to over-concentrate their ammonia solutions to compensate for what could be lost in transportation and storage. Russians are similar to Americans in being very litigious. There's actually a case currently in Russia in which a man installed a cryptocurrency wallet application on his iPhone and received a transmission of a currency called gay coin. Now, he asserts that this transaction, along with a message which was kind of to the effect of "don't knock it until you've tried it," caused a change in his personal behavior, and he's claiming damages for this. And he's, of course, suing the app producer and the user who sent him the message, but mainly he's concentrated on suing Apple itself because they have the deepest pockets, so he really wants to get money out of them. In general, Russians are suspicious of the quality of manufactured products, and when I first came to Russia, I went to a hardware store to get things for a new apartment I had rented. I needed a wastebasket, a vacuum cleaner, a mop, a broom and dustpan, those sorts of things. And when I was at the checkout, I noticed an elderly woman who had been, unscrewing a light bulb from near the register, and I thought she was perhaps stealing it, but she actually proceeded to use the socket from the light bulb to test every one of the 20 or so light bulbs in her basket. And only once she was satisfied that they all worked, she replaced the store's light bulb and then went to the register with her tested light bulbs. It's much like you might inspect an egg carton to make sure that none of the eggs are broken. The Russians just always on the lookout for someone who might rip them off for a negligible amount of money. And therefore, it's my experience that Russian ammonia manufacturers will usually give you a bit extra, because they know that if they don't, someone will come and complain about how his ammonia solution was 24.9% rather than 25% concentrated, and they'll show up at your headquarters with a fraud lawsuit over half a penny of missing ammonia. So it's possible to standardize ammonia solutions with hydrometers, but this isn't very sensitive because the density of ammonia is close to that of water, and also I refrigerate my ammonia solution, so it's rather a pain to do densitometry when the temperature is constantly changing. There's actually a fierce debate in the chemistry world about whether or not ammonia solutions should be refrigerated, but I choose to refrigerate mine. As we all know, there is a shortage of inane conflicts going on right now in the world, so if you're looking for one to follow, the question over whether or not aqueous ammonia solution should be refrigerated or left at room temperature is certainly one you can follow. In any case, in the later section of this recording, I will be demonstrating the synthesis of this ammonia salt through titration and pH measurement. The second reagent we'll be working with is ferric chloride hexahydrate, or iron 3 chloride hexahydrate. Now, I've measured this out into a beaker as opposed to laying it out on a piece of paper as I've done with some other reagents, because this compound is incredibly hygroscopic as well as rather corrosive. As you can see, it absorbs water from the atmosphere and turns into a sort of orange-brown acidic sludge almost immediately. And because there's an equilibrium between the anhydrous and volatile diferric hexachloride, which has some covalent characters, it also has a rather terrible smell. It has a bit of a musty odor, like most volatile compounds of transition metals. Nickel carbonyl comes immediately to mind. Now, the third reagent is potassium ferrocyanide, also called potassium iron 3 hexacyanide, or hexacyanoferrate. And this is a nice, well-behaved compound. In terms of water, this is really just simple Russian tap water that I'll be using. It's perfectly safe to drink. In fact, I've been drinking it for years and is completely adequate for the cyanotype process. This process is not particularly sensitive. One of the advantages in not containing silver salts, in addition to being much cheaper, is that you don't typically need to worry about distilled or deionized water. First, we'll put our ammonium oxalate into solution. You can see these beautiful kind of needle-like crystals. I'm going to dissolve them in 25 milliliters approximately of simple tap water. Just go into solution right like this. Very easily, very soluble, as you would expect for most ammonium salts. I'm very pleased with how these turned out, actually. It's a simple reaction, but still it's nice to get a positive result from it. The crystals are also fairly physically soft, even though they look a bit needle-like, which is pretty typical of salts of organic compounds, and so you can also crush them up a bit with a stir rod to help them get into solution. The addition of water to these is actually somewhat endothermic, and so you can feel a bit of an ice pack effect, similar to what you would experience if you're dissolving ammonium nitrate into solution, although it's certainly not as noticeable as that. It's not as endothermic. The next step is to put our ferric chloride hexahydrate into solution. You can see that it's already absorbing quite a bit of water from the atmosphere, so it certainly wants to be in solution. And I'll add, again, approximately 25 milliliters here. I'll be much more precise when I'm going through the process in detail, but just in this case, I want to do things quickly to provide a demonstration. And you can see definite evidence of change in density of water. So you put this into solution. It also is more lightly colored, I would say, in solution than you would expect based upon just seeing the crystals of the hexahydrate. And when pure, these crystals are actually rather physically solid and somewhat hard to break up, but once they start absorbing water from the atmosphere, which they do, quite readily, they just become rather mushy. You can see a bit of a sickly yellow solution here. This solution is a bit turbid, and that is a result of small amounts of sulfate and carbonate precipitating out, iron sulfates and carbonates from the use of tap water, but this isn't a major concern, and these won't interfere in any way with the later steps of the reaction. Now it's time for us to mix our ferric chloride with ammonium oxalate to form ferric ammonium oxalate, and I'll take this beaker and turn this to the side a bit so that you're able to get a better view of it through the clear glass without the label in the way. There's our ferric chloride hexahydrate, although it's all hydrate now, I suppose. And here is our ammonium oxalate. You can see a definite color change as the iron ions are complexed. It's a beautiful lime green compound, our ferric ammonium oxalate. And as a note, this is the point at which the reaction becomes, or which the reaction mixture becomes photosensitive. As soon as you have a situation where you have a carboxylic acid, a reducing acid, in this case oxalic acid or a salt thereof, in this case oxalate, in contact with an iron 3 compound, then you're going to get into a situation where that iron 3 can be reduced to iron 2 by ultraviolet light, and also by blue light to a certain degree. And so this is a reaction that I would typically perform in the dark if I was preparing this for myself, or at the very least under red light. But this is under light-emitting diodes, LEDs, for lighting, and so this should be okay for a short period of time. But in the later sections of this recording, I'll go in detail into the considerations regarding lighting of the laboratory space when preparing these compounds. Now it's time for us to put our potassium ferrocyanide into solution, and I'll be putting this into a solution of 50 milliliters approximately of water. The Russians actually call this compound krasnaya krovyanaya sol, which is something like krovyanaya would be bloody. It comes from krov, meaning blood, so this would be something like red bloody salt. Not really blood red salt, it really is a bloody salt, although bloody isn't used as an insult or a term of exclamation in Russian as it is in English, or at least in Angloid English. But they do call it this, and I think it's rather a strange term because neither the compound really nor its solutions, at least in water, look much like blood. I mean, here you can see a much kind of paler yellow color with a hint of orange. I think it really is far too neon, far too pastel to really resemble blood. If anything, I think it's iron 3 oxide, ferric oxide, kind of rust or red iron oxide that resembles blood when it's in the suspension, but this is what the Russians call it. Now, and finally, it's time for us to combine these two solutions together. First, we'll pour in our beautiful potassium ferrocyanide solution, which does not look at all like blood, despite Russians calling it krasnaya krovyanaya sol. And now our ferric ammonium oxalate solution. And I'll again turn the beaker to the side so that you can see the mixing better without the label in the way. Now there is no apparent reaction here, and that's actually desirable. If this had turned blue, that would indicate that the sensitizer is effectively already exposed or already spent, because that would mean that light has already started reducing the ferric, the +3 iron to ferrous or +2 iron in the solution, and then as soon as that ferrous rather than ferric ammonium oxalate would come into contact with potassium ferricyanide, then you would get the mixed +2 +3, the mixed ferrous-ferric cyanide complex, which is Prussian blue. So even though you won't visually notice it, if your ferric ammonium oxalate is light damaged or exposed effectively, when it's in isolation, as soon as you add it to the potassium ferrocyanide, you will notice. Now that we have our sensitizer prepared, it's time to apply it to a piece of paper, and I'm actually using the same piece of watercolor paper that I used for contrast underneath the beakers in the previous section of this recording. Why waste something? And so I'm simply going to apply this sensitizer with a simple paintbrush. This is the kind of brush that you would find in any hardware store. It's a bit too large for this beaker, unfortunately, so not particularly convenient. But I'll just brush this on, and I would say with cyanotype solutions, I've found that less does tend to be more. I have tried, using the saturation method, essentially completely soaking the papers in the cyanotype solution, but what I find is that in areas where the solution is denser, that tends to produce a lot less sensitivity, although you do get a bit more tonal range there, a bit more dynamic range, and so it is a bit of a balance, but in general I would say the tendency is to oversaturate rather than undersaturate papers with the cyanotype solution. And this will, form Prussian blue and stain your hands. I would say it's less of a stain agent, certainly, than silver-based solutions, silver halides or silver nitrate or so on and so forth, silver bromide, but still certainly does have that effect. Now, typically the paper is dry, but what I'm going to do in this case is actually demonstrate the creation of a print in real time. In order to do so, I'm going to need some ultraviolet glasses, and I found these to be, generally quite effective. I do have welding goggles, which I use if I'm using a more powerful lamp than this. This is around 20 watts, and I do have a lamp that is around 500 watts, or a lamp array that's around 500 watts, but these will be sufficient here. So I'll simply put these on, get my lamp, and we can make a cyanotype print in real time. I'm now going to turn on this lamp and quickly put my hand over the cyanotype paper. Now, typically what happens with cyanotype development is that, or cyanotype exposure, I suppose I should say, is that you don't actually see the color change that rapidly. And the reason for that, or you don't see it that rapidly until you put it in water, and the reason for that is that the reduction of ferric to ferrous, the reduction of iron 3 to iron 2 with the oxalate salt is occurring, but Prussian blue isn't actually formed in dry paper, because even though those iron 2 plus ions are being formed, they aren't actually going ahead and reaching the potassium ferrocyanide, the iron 3 ions, so they don't actually perform the reaction necessary to produce Prussian blue until the print is actually soaked in water, in which case the ferrous ions are mobilized and they can find their ferric ion counterparts and start actually forming the Prussian blue, which is then what you see. But in this particular case, because this surface, this substrate is still wet with the solution, I haven't waited for it to dry, there still is significant mobility of ferrous ions, and they can actually go right ahead and start forming that Prussian blue, which is what you can see here in this paper. So I'll certainly need to shut this lamp off, before I remove my hand, or else I'll expose over the unexposed parts. But as you can see here, in just a minute or two, there already is a significant print, and this is really only from 20 watts of ultraviolet light, mostly around 185 nanometers, with some 250 or so nanometer portions of the wavelength as well. And that is a cyanotype. Now, of course, the cyanotype we produced is not itself light stable. If this is exposed to ultraviolet light, either from a lamp like this or from sunlight, it will be ruined and the unexposed areas will be exposed. So to fix it, we simply need to dip it in plain water. And this is something for which you might want to roll up your sleeves and put your tie behind your back just to make sure that you don't get any of this solution on you. But all we need to do is to remove the chemicals that we added to the paper, which is the ferric ammonium oxalate and the potassium ferrocyanide, and those chemicals are water soluble. That's, after all, how we got them into the paper in the first place, by applying them in aqueous solution, and so we can simply remove those unreacted chemicals with water as a solvent, just as we used water as a solvent to get them onto the paper. And there's no special requirement for this water. I find tap water perfectly adequate. You could probably use a stream or a fountain if there's, flowing water that's convenient in your area. That's probably ideal. Could make the washing a bit easier. We simply need to wash this out. Another advantage to painting on the cyanotype solution rather than soaking it into the paper is I find it's much easier to fix. You have less of an issue with residual chemicals that kind of stay behind. It can be difficult to remove. Now, if I were doing this in some, quote-unquote professional capacity, I would run multiple washes, but you can see here we have a cyanotype print of my left hand right there. And it is now fixed and light stable. A simple process. The classic application of the cyanotype process is not in creating pictures of my hand, or really of anyone's hands. Actually, the most common usage historically, and I would say as well currently, is in imaging botanicals and before digital photography, if you can call it photography. I think that photogrammetry would be a better description. But in any case, before digital technologies, cyanotypes were used to document plant species, which made them a very important technology in mid-1800s botany. The cyanotype process has several important advantages here. It's cheap, it's relatively non-toxic, it's easy to prepare and store and use in the field. It reproduces specimens at a 1-to-1 ratio, and it allows you to create copies at scale. You can even use it to image living plants without removing their leaves or other organs, so it can be a non-destructive method. And we'll cover this in later sections of the recording. In this case, however, I did, as you can see here, harvest a few plants, so indeed plants were harmed in the making of this recording. Under the light of the moon, the American stalks the streets of Moscow, driven by an inhuman hunger, a vegetarian bloodthirst. Or would that be phloem thirst? He prepares his gruesome tools. No garden is safe. But in any case, if you arose this morning and noticed that one of your fern fronds was missing, mea culpa, mea culpa. This is a frond of Madarusia strythopteris, often called the ostrich fern, although I don't really see the resemblance particularly. I suppose this frond a bit resembles the tail feathers of an ostrich, Struthiocamelus, but honestly, I think it's much more similar to the plumes of a secretary bird or something like that. This branching that you see in the leaf tissue is intended to increase the surface area for photosynthesis, and that's, I suppose, the same evolutionary pressure that is applied to feathers to have a large surface area to enable flight with maximum strength and minimal weight. So in truth, I think it would make more sense to compare the structure of this fern to the feather of a bird that can actually fly, which is, of course, most of them. The Russians call this species Strausnik obyknovieny, from Strauss, or Strausnik, which is like little ostrich. It's the diminutive of ostrich. In Russian, you'll find that diminutive forms of words are often used for living things. For example, kuznets is a blacksmith. It's a type of job. But a kuznechik, or a little kuznets, is a grasshopper. Obyknovieny means typical or regular, because this is the type of fern that grows commonly in Russia, from obychna, normal. Something you'll notice about this frond, especially if you look at the back, is that it's in fact sterile. You can see that if you look at the undersides of the leaves. You see, when I was thinking of what sort of plants to harvest, I thought a fern would be a good choice because in the land of my birth, we mainly have ferns which include sori on the back. The singular would be sorus. And these are the little brown dots that you often see. They contain sporangia, which are the haploid reproductive cells of the plant, in this case of the fern. And I thought that this fern would likely have those, and they would come through on the cyanotype. You would be able to see some texture there with the sporangia, so we'd get a bit of a more interesting print. But it turns out that Madatusia struthoropteris, this particular fern, has a characteristic where only certain of the fronds are reproductive, and they actually grow only later in the season. So the frond that I have is fully diploid. It's not a reproductive frond of the fern. The ferns I grew up with in the Pacific Northwest are primarily Polysticum municium, which is called the western sword fern. Russians call those ferns that grow in the Northwest the mnogoryadnik zashishony, which comes from mnoga, which means many, and zashishony means something like protected. It comes from zashita, which means kind of protection from danger. But in the case of zashishony, we have the adjectival form. It's actually very funny, I think, because zashishaisia, which literally means something like, protect yourself, is what Russians shout when starting a sword duel. In English, we usually use just the French phrase or the French words en garde, but the Russians have their own term, which is zashishaisia. So the term zashishony, which is part of the description of the western sword fern in Russian, meaning protected, it comes from the fact in Russian, the etymology in Russian comes from the fact that these ferns don't really grow well in Russia. It's too cold for them, so they need to be grown in greenhouses to protect them from the cold, unlike ferns native to Russia, like this one, which can grow, bez zashiti, unprotected, just out in the ocean, out in the open, because they've evolved to tolerate the cold. But it's quite funny, isn't it, that by coincidence, the Russians call the fern, this what we would call a sword fern, the protected fern, because you need to protect it with the greenhouse. But the Americans call it the sword fern, and this phrase, защищайся, protect yourself, is exactly what you would say when starting a sword fight in Russia or a duel of some sort. I've actually been chuckling at this for probably around 10 minutes now. Anyway, I also collected this plant you can see here. This is Citrata maculata. I got it from Sokolnikov, which is a park in a kind of swampy area of Moscow, and I harvested it from relatively swampy land, which was near a pond. In English, this plant actually has quite a number of names. Let me just rearrange this fern a bit. We call it the spotted cowbane, and it does have some spots on its leaves here. It's also sometimes called spotted parsley, even though this plant is obviously not parsley, and I don't really think it looks like parsley. Does this look like parsley to you? It doesn't to me. It also does not smell like parsley, nor is it in the same genus as parsley. I also found some sources calling it poison parsnip, even though in addition to being not parsley, it is of course also not parsnip, nor does it look like parsnip. Nor does it smell like parsnip, nor is it in the same genus as parsnip. Again, this is in the genus Cicuta, and parsnip is in the genus Pastanaca. But it gets even worse. Americans use the term poison parsnip to refer not only to this Cicuta maculata, but also to 3 other species, which are Cicuta bulbifera, Cicuta douglasii, and Cicuta virosa. Again, none of which are parsnip, and none of which are even in the same genus as parsnip. We also call all 4 of these species sometimes water hemlock, which is confusing because, again, if you say water hemlock, it's really not clear which of these you're talking about. Also, what does water mean? I mean, most plants grow in water. You could be referring to Cicuta maculata, which I have here in my hand. You could be referring to Cicuta douglasii, Cicuta bulbifera, or Cicuta virosa. Even worse, when you say water hemlock, just the fact that you said hemlock is likely to make English speakers think of Coinia maculatum, sometimes called poison hemlock, which is yet another species in another genus. There's also Oanthea crocata, sometimes called hemlock, water dropwort, which is not to be confused again with water hemlock, which is yet another species. It could also lead to confusion with certain coniferous trees, mainly native to Japan, of which there are 9 different species in the genus Pinaceae albitidae tsuga, all of which can also be called hemlock. The situation in the Russian language is also a bit confusing. Russians call this stuff vyoch patnisty, which means something like spotted hemlock, or strangely, sometimes they also call it pyatnisty cowboy, which would mean spotted cowboy. And I'm not going to go into the whole nomenclature thing again for Russian, in part because I think the Russian terminology isn't as bad as the English, but there are a lot of aspects of the naming of this plant which are also confusing in Russian, particularly with regards to mixing it up with other species that are called hemlock, as well as actually mixing it up with some species in the marijuana family, including Cannabis sativa, Cannabis indica, and Cannabis ruderalis, as well as a number of species in the carrot family, especially Dacus carata sativus. So this is my plea: biologists, botanists, linguists, American and Russian, please lend me your ears. We need to overhaul the nomenclature for these species. We need clear, distinct, descriptive, and certainly unique names for all of these species, because it's very easy to mix one up with the other. I chose these specific plants for a reason. I chose this Marusia struthoropteris because ferns are among the earliest plants to colonize the earth, and the cyanotype is one of the earliest photographic processes, so the pairing seems, to me at least, appropriate. And I chose this Cicuta maculata because it produces an interesting compound, circuitoxin, which is in fact psychoactive. Specifically, it blocks your GABA receptors. Despite this molecule, I think, not looking drug-like in most respects. It's a strange diol. It has a number of conjugated acetylene groups, and it's highly unsaturated. So it's not an alkaloid, but it shows alkaloid-like properties. In In the same sense, the cyanotype process uses ferric ions as an oxidizer, which also seems quite strange because we're not used to thinking of ferric ions as being particularly strongly oxidizing. Instead, it's really iron, or iron in the form of steel, that's what gets oxidized to ferric oxide or rust. And yes, ferric oxide can be an oxidizer in some cases. Probably the most spectacular would be the thermite reaction. And the most important, at least economically and practically, is the reduction to iron metal in iron blast furnaces. But these reactions take place under quite extreme conditions. So yes, ferric ions will act as oxidizers if you heat them up to glowing and blast them with carbon monoxide at 800 degrees Celsius. So we have one of the earliest photographic processes and one of the earliest plants to colonize the land. We have a photographic process which exploits the counterintuitive reduction of ferric ions, and we have a plant which produces a compound that is counterintuitively psychoactive despite not having many of the molecular traits we would associate with that. So I think this is quite an appropriate pairing for cyanotypes. I also chose these because they're relatively flat. I mean, most leaves are flat, or at least are amenable to flattening. Of course, I know the pedants will point out, oh, what about the spines of cacti? Aren't those technically leaves? Yes, they are. Or what about the thorns of roses? Aren't those technically leaves? And yes, they are. But these leaves are flat. They're adapted to photosynthesis, and I think they'll be easy to flatten out nicely. And these Cicuta maculatum flowers are fairly small as flowers grow, as flowers go, and I think we'll also be able to flatten them out quite nicely. In making this print, first we'll coat the paper just as I did when imaging my hand. As you can see, I planned a bit better this time, and I poured the cyanotype solution into a larger beaker so that my paintbrush will fit more conveniently into it. Now that we have our paper nicely coated, we can simply arrange our botanicals on top of it to create the composition we've decided we want. I think I'll lay the fern like this. You can see I've sandwiched these under a plate of glass, and this is a plate from a simple glass picture frame which came from Cyanotype, which is a chain of Russian stores that are roughly equivalent to dollar stores, I suppose. I imagine they'd be equivalent to Dollar General. I don't think I've visited a dollar store in the United States very recently, so I suppose I wouldn't know, but I would imagine that that would be the case. Cyanotype literally means silly prices or funny prices. And I find that the cheaper the picture frame, as long as it does have, a solid piece of glass, generally the better, because cheaper frames have thinner glass typically, and that will block less of the ultraviolet. Another nice thing about using the frames is that they have, of course, this little stand at the back, which helps you if you're photographing or cyanotyping outside to get the frame at an appropriate angle towards the sun. So I'll simply replace this in the frame, putting the glass back in from whence it came. You can see this frame also has these little brackets here, which will help to put pressure onto the cyanotype subjects to keep them a bit better pressed against the glass and hopefully result in a sharper print as a result. There we go, ready for printing. When I print this, I'm going to stand it up and actually also use the stand I have here for my ultraviolet lamp. There are really two reasons for this. The first is that in terms of image quality, it's better to have a lamp in a fixed position so that all of the rays from it are coming at the same angle, because this will minimize any blurring you get as a result of the fact that your cyanotype subjects are never going to be perfectly flat against the paper. Pragmatically also, even though these glasses provide a decent amount of resistance to ultraviolet, it's not the sort of thing you really want to test, and you always want to minimize your exposure to any UV sources, or at least artificial UV sources. So that's another advantage for me in terms of managing the exposure. I think that'll do very nicely, so let's begin our exposure under ultraviolet. I'm going to bring the camera in closer so you can see more of the development take place in real time. Okay, I think that likely does it, so now I can shut off the ultraviolet lamp we've been using. Take off my eye protection. Move the lamp out of the way for a moment. Move this first. There we go. And now let's see how the result looks. I suppose you'll see this before I will. So I take the glass off. And look at that. That's our cyanotype. We can now wash it and go ahead and fix it, but I think this already looks beautiful. Given that the cyanotype process is a negative process, it can also be used to create prints from photographic negatives. This is because printing is effectively equivalent to multiplication, and you know what they say, 2 wrongs don't make a right, but 3 lefts do. And similarly, a negative print of a negative will be a positive. Typically, this is a contact printing process, since darkroom enlargers that you'll find in labs rarely have the high-powered ultraviolet lamps that would be necessary for enlargement, and it's a contact print that I'll be demonstrating here. I've seen numerous demonstrations of cyanotype contact printing online, and in 99% of the cases, the process involves taking a digital photograph with a digital camera, bringing it into Adobe Photoshop or some similar tool, rendering it to black and white, inverting it then to create a negative, printing it out with a regular printer on transparency sheets, which are basically sheets of plastic, and then placing these sheets over some cyanotype substrate, usually a sensitized piece of paper. Now, personally, I find this to be rather silly. Yes, it's something that one can do, and it can work, but it doesn't make much sense to me. Nigel Braun's recording of cyanotype printing is an excellent example of this print a negative with a printer process. And while I think the recording overall is excellent, and I don't want to spit on him in any regard, he's an excellent chemist, I do think the process is a peculiar choice. There's a meme template, in fact, along the lines of, I created item X by using items A, B, C, and X, where the item that's ostensibly being created actually requires itself as an ingredient or component. An example would be, I created my own refrigerator using just a propane tank, copper piping, an old car radiator, and a refrigerator. So what Braun has done is essentially printing a photograph using citric acid, ferric chloride, aqueous ammonia, potassium ferrocyanide, and a photo printer. Another example in chemistry would be Cody Reeder's demonstration of the chamber process for sulfuric acid synthesis, in which he in fact uses sulfuric acid as a starting ingredient for the production of sulfur dioxide, effectively using sulfuric acid to create sulfuric acid. Again, nothing against these men. They're both excellent chemists, each individually far more accomplished than myself, but I am taking a different route. One of the major advantages of the cyanotype process is that it requires no electricity, at least if you use the sun as your light source. And as soon as you bring digital photography and Photoshop and digital printers into your workflow, you've forfeited really that benefit. And for what? For a photographic print, which is going to be limited not only by the resolution of the original digital photograph, but also by the resolution of your printer. Do you want JPEG artifacts in your cyanotype? Do you want inkjet smudges on your print? Well, I certainly don't. I've generally had poor experiences with printers as well, and I'll quote Matthew Inman on the topic. Printers, unlike other technologies, are remarkable in the fact that they are just as crappy and unreliable today as they were 30 years ago in 1995. Yep. Or, printer driver disks are older than the Earth itself, so you'll have to install new ones. Would you like to download crapprinterbundle.exe? In addition to the drivers for your printer, we'll install a massive suite of worthless multimedia applications that will run in the background forever. Yep, right on. Or, printers are great for photos, as long as you only need to print 1 photo per year. And yes, this is my experience precisely. So bravo, Mr. Inman. I couldn't have said it better myself, which is why I didn't say it myself. I chose to quote you instead. For these reasons, it makes much more sense to keep the cyanotype printing process completely in the realm of chemical photography and completely in the realm of optical printing. Even a run-of-the-mill, decades-old lens, such as this, can achieve far higher resolutions than digital cameras and printers, and honestly, the limiting factor in almost every case is going, of course, to be your technique. That's certainly the case for me. So a full optical process will dramatically increase the upper limit on quality that you can achieve. Control over depth of field, resolution, dynamic range, and so on. In order to produce negatives of appropriate size, you can use ordinary black and white film in a large format camera. This is some Kodak 100T Max. I typically think Triax is better, especially in large formats, but this is what was available in Russia secondhand. For example, you can use a 4x5 camera such as this. It's quite handy, collapses quite nicely. Or if you want to go a bit bigger, you could also use an 8x10 camera such as this. This is actually technically 10x12, but I use it as an 8x10 most of the time with film holders which are scaled down to accept 8x10 film. You get much better results that way, and if you use the sun as your light source, which I know I'm not doing here, but I could, you can keep the process completely electricity-free. So why suffer the inconvenience of needing to use electricity and having to have a photo printer when you could simply carry something like this around with you every time you want to take a picture? In truth, I usually don't carry this entirely myself because the camera and especially the lenses are so heavy and so bulky that it becomes a bit impractical for just one person to carry them. So usually I'll disassemble this and have, one person carry the lens, one person carry the camera, and then in terms of accessories like a tripod, which you'll obviously need, and a focusing loop, of course, the film itself and the film holders for it, as well as the dark cloth, which you'll need to put over your head for actual focusing. You can just figure out, kind of draw straws perhaps on who will carry those accessories. You may also, especially if you have plans to photograph over a long period of time or you have a lot of film, you may also want to pack with you some sort of portable light-tight tent or a dark tent, sort of like a dark room, but a portable dark room for changing film. And I find that a TP design made with the same sort of leather as I typically use for my dark cloth when I'm focusing is quite effective for that. So you can also have someone carry a tent around with you. Here is a 4x5 inch or 4x5 inch size black and white film negative that I've shot with this exact camera. I'll zoom in and invert this so you'll be able to see what it should look like roughly when we print it out. I've inverted this footage, so you should have a good sense of what this negative should look like roughly when printed out, although of course rather than being in black and white, it will be in corduroy blue and white or Prussian blue and white. If you handle negatives frequently in photography, then you have a good instinct for what a negative will typically look like when inverted to positive, but in case you for some reason haven't been around photographing negatives a lot, I've decided to invert this footage so that you'll have a better sense of what we should get as an end product. I've previously coated and dried this piece of cyanotype paper so the solution won't be liquid and won't stain the negative, and then we'll simply contact print from this negative onto this. And you know what, let's get a bit artsy. Why not do a bit of mixed media? Here I have some different plants that we can lay on top of the paper to create a decorative border, since this 4x5 inch negative, as you can see, is quite a bit smaller than my cyanotype paper. Right here, I have a sample of Oxalis spiralis zinfandel, which is really quite the species name. You've got the Oxalis spiralis, that's a nice rhyme, and then you have the zinfandel, and I suppose these rather do have a wine-like color. This plant is known in English as spiral sorrel. I've asked Russians what this is called, and they tell me it's krasny klever, which literally translated means red clover. I haven't actually been able to find, any kind of written document about this, so I've just been going around to kind of people who sell plants basically in the markets and asking them what this is, and that's what they say. The krasny klever makes it sound like this is clover, but in fact it's not. This is a true clover, which is what Russians call lugovoy klever, or meadow clover, garden clover, or something like that. In this case, we have a fierce international competition regarding who can come up with the worst naming convention, because Americans call this spiral sorrel without it actually being a type of sorrel, and Russians call it krasny klever, or red clover, without it actually being a type of clover. True clovers, such as this, are in the genus Trifolium. They are legumes, they're nitrogen-fixing, they have, nodules with symbiotic bacteria that do that in their roots, and they're related to beans and peas, whereas wood sorrels, like this, are in the genus Oxalis. They are not legumes, they are not nitrogen-fixing, and rather than being closely related to beans and peas, they're actually closely related to a group of plants we call in English sour grasses, which, confusingly, are not actually grasses. True sorrels, not wood sorrels, but just sorrels, actually sorrels, which I sadly don't have an example of, are in the genus Rumex and are related to rhubarb and to buckwheat. Even worse, Americans also use the term sorrel to refer to roselle, which is another unrelated plant that is actually a type of hibiscus, specifically Hibiscus sabdarifa. I don't have a sample of it here, but I'll put an image of it up on screen. Now, I've chosen to include this plant in the printing process because members of the genus Oxalis produce significant amounts of oxalic acid, and oxalic acid is so called precisely because it was, in fact, originally derived from this specific genus. Now, given that I have this nice sample here of Oxalis spiralis zinfandel, it would be a shame, I think, not to get better acquainted with this. I took this from someone's garden along a busy path, so hopefully not too many dogs have pissed on it. I did pick it during a rainstorm, so hopefully the rain has washed away any remaining dog piss. And I also washed it with soap and then with water and then with 96% azeotropic ethanol, so hopefully it's reasonably clean. So I think it would be reasonable to, take this Oxalis spiralis zinfandel and give it a taste. Well, it certainly does have a carboxylic acid flavor. Usually I appreciate the taste of carboxylic acids and also in general. Yuck. Usually I appreciate the taste of carboxylic acids and usually the smell as well if they're volatile, but oxalic acid, I would say this stuff is, simply a bit too strong. There's also a very unpleasant bitterness, which I assume is coming from tannins, tannic acid, and so on. And another aspect of consuming plants that contain oxalic acid, which is not really a matter of taste exactly, but it does affect the experience because it's a matter of texture, is that oxalic acid is a very strong and effective chelating agent for calcium 2+. And since there's calcium 2+ in your nervous system and your mucosa and your blood and so on, it will start chelating out that calcium and forming calcium oxalate crystals, which are very granular and sharp. It takes on, in general, a very gritty texture, and these calcium oxalate crystals are also quite sharp, so it's a bit like eating overall bitter, sour, burning sand, and I still have some of that sensation in my mouth, which is not particularly comfortable. It resembles, I would say, the sharpness of Utrisha diorsa, or the stinging nettle. Russians call this plant krapiva, and while stinging nettles are perfectly pleasant to eat if they're properly prepared, the truth is that preparing them is a bit difficult and rather time-consuming and labor-intensive, so it's often not done perfectly. And if it's not done perfectly, those little trichomes that have histamine in them will penetrate your oral mucosa, and they're sharp, so it's not something too enjoyable. And there's something similar, I would say, from eating this Oxalis spiralis zinfandel. You can kind of feel the sharpness. It's not coming from trichomes, it's coming from that calcium oxalate, which is precipitating out, but it is similarly unpleasant, and that's what I was experiencing here. I've had the experience in Russia several times in which I'm eating something that's a bit suspect, usually for social reasons, and I feel some kind of internal conflict. Because on the one hand, if I swallow it whole, or at least, as whole as I possibly can, I don't need to taste it. But on the same note, the more that I chew it, the more surface area I will produce, and that will allow my stomach acid to get better purchase on whatever, microorganisms might be there. So chewing a suspect food thoroughly, although certainly is much less pleasant in a gustatory sense than swallowing it whole, is a type of investment in one's future. It's an investment that means less time likely to be spent in gastrointestinal distress. So it really is a conundrum. But in this case, it wasn't a conundrum because I'm under no social pressure to consume this stuff or to avoid spitting it out. And so I simply did so. It was yuck, quite unpleasant. I'll also say it's a good idea to be cautious if you're handling chelating agents in general. These agents do have some medical uses, particularly in treating heavy metal poisoning, and also there's some genetic iron overload diseases and copper overload diseases where chelating agents can help to cut down on absorption and get some of these metals out of your body if they're present in excessive amounts. But you really do need to be careful with these, especially if they are capable of chelating important metal ions that are biologically relevant in humans. So, for example, oxalate salts and oxalic acid will tend to chelate away your calcium. EDTA, ethylene diamine tetracetic acid, typically goes for magnesium too. It can also bind your cobalt. Dimercaprol and other 1,2-thiols tend to go for your iron and sometimes your vanadium also. Calcium oxalate crystals, which can occur in your kidneys if you consume too much oxalic acid, will cause kidney stones. But more concerningly and more immediately, because calcium has an important role, even a dominant role in nerve transmission, you can in fact develop a neurotoxicity or central nervous system symptoms from hypocalcemia. Your body does have the ability with osteoclasts to effectively mobilize some calcium from your bones, but the rate of that process is fairly limited, and so it's possible to consume so much of a chelating agent that your body won't be able to keep up with the depletion of calcium in your nervous system, and that's certainly a situation you want to avoid. So remember to be careful with chelating agents, especially for biologically relevant metal ions, and I would say especially for calcium. Here I have my piece of sensitized paper, and although normally I would be working under safe light, I'll be working in normal studio lighting and just work quickly to get this negative printed onto it. So I think I'll place the negative in the center with the emulsion side down. Let's see. That would be the emulsion side. And I'll be placing some of these lovely little plants on top of it. I can overlap them as well. There's no reason not to. These plants have a bit of an annoying habit, which is that they only really open during the daytime and when it's sunny out. So they have a sort of rhythm related to that. And I had to shoot this during the afternoon and evening so that it wouldn't interfere with my work. And because of that, I had a bit of trouble because these were always closed during that time. So I brought some inside and forced them to adjust to the new circadian rhythm, rather opposite the circadian rhythm that they were used to. But some of them actually died. They seemed very unhappy about having to make that particular adjustment so quickly. But ultimately, the majority of them did survive and did make that adjustment, and so I'm able to handle them here. They think right now is during the day, even though it's in the afternoon, and they are open and showing their leaves. Oxalis spiralis zinfandel. Again, what an absolutely gorgeous name for the species. Now that I have my composition prepared, I'll slide under it this piece of particle board, which will act as the holder. And then I'll sandwich a piece of glass on top of it. This piece of glass I've taped off with electrical tape so that it's a bit easier to handle, so the edges aren't so sharp. That does, of course, make it a bit wider because the tape is a dimensional material, but fortunately, this is such a cheap frame that it has rather sloppy tolerances, and so this isn't a problem in terms of actually fitting it into the frame. I've secured the pressure clips, and now it's time for exposure. We are now prepared to begin our exposure. As you can see, I've got my ultraviolet safety glasses on, and although it probably appears from the perspective of the camera that this lamp is located around here above the picture frame. In fact, it's located roughly equidistant from the middle of it. Now I've removed all of our oxalis borealis zinfandel, and you can see the print where the negative was held up against the paper along with the shadows, effectively, of the oxalis borealis zinfandel flowers that we placed on top of it, or leaves we placed on top of it. The cyanotype process is some hybrid between a printing out and a developing out process. I will take an image of this closer up so you can see what it looks like before we start developing it with water. And now we will develop the image out with plain water. You can see significant darkening already. And there we are. Now, with the introduction over, let's get into the chemistry of cyanotypes. There are two common processes as of 2025, which is the year of this recording. The first is the classic process invented by Sir John Fredrick William Herschel in 1842. Like all great men, Herschel stood on the shoulders of giants. His work relied on Johann Wolfgang Goberreiner's earlier 1831 discovery of the photoreduction of ferric ions to ferrous ions by carboxylic acid salts. And in terms of actually obtaining the potassium ferrocyanide needed for the process, he relied upon the electrochemical work of Alfred Smee from 1840. Much of the popularization and early use of the cyanotype can be credited to Anna Atkins, who in 1843 produced photographs of various nautical and terrestrial plants and created the first books illustrated with photographic replicas. Her work is phenomenal, and I think her cyanotypes hold up well even 200 years later. I'll put some on the screen for you to admire. They're all out of copyright by this point. I think these are great, so good job to Atkins. She really did the impossible. She made England look beautiful. We also need to give credit to Robert Bingham, who wrote the first widely published description of the cyanotype in his book. Photogenic manipulation, the theory and plain instructions in the art of photography, or the production of pictures through the agency of light, including calotype, fluorotype, chromotype, chrysotype, cyanotype, calicisotype, and anthrotype by Robert J. Bingham, chemical assistant in the laboratory at the London Institution, 5th edition. That's quite a mouthful, especially since Bingham included his own name in the title of his book, so I'll hereafter refer to it just as Bingham's Photogenic Manipulation, 5th edition. This is a very uneven source, although technically a different book, but part of the same series. Bingham also wrote a resource on daguerreotypes, which is quite good in my opinion. The section on cyanotypes, however, is quite lacking. I'll show some pages I've scanned for my copy of this book. This is out of copyright again, so it should be fine. Bingham writes, Sir John William Herschel is also the originator of this process, referring to cyanotypes, or rather a number of processes, for it includes all pictures taken with salts of iron, particularly in combination with cyanogen, unquote. And I think this is an extremely misleading introduction. First of all, I don't think it's fair to give credit for every photographic process that involves iron to Herschel. Now, Herschel was a great and accomplished chemist, but photography is such a huge field that you can't just claim an entire chemical element for yourself. Not even something obscure like some weird-ass lanthanide, and definitely not iron, which is used in everything, not just in photography. Now, claiming all pictures taken with salts of iron is not as greedy as claiming, all pictures taken with salts of silver, but still it's quite pompous, or I suppose really it's not Herschel himself being pompous, it's Bingham heaping too much praise upon him. And Herschel certainly deserves a lot of praise, but still you can heap too much praise onto someone even if they do deserve a good amount of praise. Bingham even describes another process involving iron, which he calls the ferrotype, and also calls an energeotype, based upon the idea that the effect is not caused by light, but by energia. What is energia, you ask? Well, it's a peculiar principle, according to Bingham's work. That's not very helpful, since energia just sounds like energy, and light, of course, is a form of energy. So energia type as the name for a photographic process is just like saying light type, but producing images with light is what photography is all about. So this is a very silly name. What Bingham calls a ferrotype or an energia type is what we would call a tin type. And arguably our nomenclature isn't much better because tin types are a silver-based process and they don't actually involve tin metal or tin compounds in any way. I'll note that this whole energia type nonsense didn't come from Bingham. He's just reporting on it. This is the actual nomenclature that came from Robert Hunt. Fortunately, we stopped using this term by the early 1850s. This isn't a recording about energia types, aka ferrotypes, aka tin types, but in any case, that process involves what Bingham calls protosulfate of iron, that is ferrous sulfate, really probably some hydrate of ferrous sulfate. So Bingham should certainly know better than to say that all pictures taken with salts of iron are cyanotypes, since he himself describes a process involving salts of iron that is explicitly not a cyanotype. The second issue that I have with this description is the reference to salts of iron in combination with cyanogen. Now, if you're hearing this, you're probably thinking about actual cyanogen, C2N2, basically two cyanides joined at the carbon. You could also think of cyanogen as the nitrile of hydrogen cyanide. This substance is a gas at standard temperature and pressure, and it's the diatomic pseudohalogen form of the cyanide ion. You can think of having potassium chloride or potassium cyanide. You can either have the chloride ion or the cyanide ion, and you could have the corresponding acid, which would be hydrochloric acid in the case of potassium chloride, or hydrogen cyanide in the case of potassium cyanide. And then if you oxidize that acid, if you abstract the hydrogen and join, two halogens or pseudohalogens together, you get chlorine gas, or equivalently cyanogen gas. You can think of cyanogen gas as the diatomic form if cyanide was hypothetically its own atom. And in many ways, chemically, cyanide does behave as if it's its own little atom. That carbon-nitrogen triple bond is really just that strong. You can't really have a carbon atom and a nitrogen atom that are triple bonded together at neutral charge, just, hanging out, because it's a radical species. You get an unpaired electron around the carbon, and it will either grab an electron to form a cyanide ion, just grab that from somewhere and form, negatively charged cyanide, or if you just had this stuff in isolation, one carbon triple bond nitrogen will find another and they'll dimerize to form cyanogen. Cyanogen is really a nightmare to handle. It's a gas, it boils at negative 21 Celsius, so it's even more volatile than hydrogen cyanide, which boils at positive 26 Celsius. Even though cyanogen has a heavier molecular weight, 52 grams per mole as opposed to 27, so almost double. This is a great example, by the way, of how hydrogen bonding will affect physical properties a great deal. Hydrogen cyanide also has a lot higher latent heat of boiling due to the hydrogen bonding, so it's a bit like ammonia. Sure, if you have a beaker of it on a bench or something, it's going to boil away pretty quickly, but it needs to absorb lots of heat to boil, so it's not just going to all go poof and boil away like methane or something, and it doesn't have as much of a tendency to flash boil and kind of bump and spatter all over the place as something like methane or liquid nitrogen does. Cyanogen lacks this hydrogen bonding, so it's just much, much harder to handle as a liquid at normal pressure, even compared to other cryogenic liquids you might want to handle in the laboratory like that. And in addition to being much more volatile and boiling much more easily than hydrogen cyanide, it's also even more toxic and flammable. In fact, cyanogen is explosive, and it's one of a few gases that can explode even in the absence of oxygen or indeed any other oxidizer like chlorine, for example. The most commonly encountered of these gases are acetylene, which is mainly used in welding, then propylene, which is mainly used in making plastic, namely polypropylene, and ethylene oxide or oxycyclopropane, which is the intermolecular ether of cyclopropane, which is medically used for sterilizing equipment and such. You can get explosive polymerization with cyanogen, like with these other troublesome gases, so you can't store it in normal pressure vessels. In normal gas cylinders, you need to dissolve it in some kind of special solvent inside the tank, and you need special packing materials, you need special gas regulators for it. You can't allow the gas to get above a certain pressure, it will just spontaneously detonate. And there are issues where you have to be careful about the churn radii of any bends in your tubing, because if they're too tight, the gas molecules that are traveling down the tube can pick up a lot of speed, and then, when they hit a right angle, they'll just, crash into the churn in your pipe, and that will detonate them. You can also run into a lot of issues where you can get tiny amounts of solid contaminants in your gas system. This could be something like, flakes of paint, little bits of rust. Often it's pieces of metal, little tiny burrs that form on the screw threads or from turning valves on and off. It's a bit like metastatic cancer cells getting pulled into the bloodstream. You have the cyanogen gas flowing past these little bits of dust, and the center of the pipe has the fastest flow. And then by the Bernoulli principle, the center of the pipe also has the lowest pressure. So these little bits of dust, they get sucked into the flowing gas, and they can bounce around inside your piping and inside your fittings and your regulators and your valves and your manifolds. And the thing is, cyanogen is so unstable that the impacts of these little tiny, often microscopic particles can be enough to cause a detonation. I'll put some recordings on screen of testing where particle contamination has caused explosion inside gas regulators and inside storage vessels. This is high-speed footage. These were shot at tens or hundreds of thousands of frames per second. So the sequences you're seeing all took place over just tiny fractions of a second. When these sorts of events happen with reactive gases, you're never going to be able to consciously perceive the process itself or have any sense of prior warning or any ability to react. The time scale of a true explosion is so many orders of magnitude faster than human reaction time that you'll only ever consciously perceive the before and the after. There is no during from the perspective or the standpoint of human consciousness. On top of all this, cyanogen is also a major violator of the ideal gas law. And of course, no gas perfectly follows the ideal gas law because we don't live in an ideal world, although some gases get pretty close, such as helium. But cyanogen is an especially egregious violator, so as a reagent it can be very difficult to measure out the amount you want because the relationship between the temperature and the pressure and the density and the volume is really complicated. And because of this, cyanogen is just so difficult to handle that if you read the description of cyanotypes that Bingham wrote about cyanotypes involving, quote, salts of iron in combination with cyanogen, you're probably going to think to yourself, well, I'm not equipped to handle cyanogen, so that's too bad. I guess I just can't make cyanotypes then. What a pity. And that's really a shame because this is the first published source on cyanotypes. So for many people, it's likely that they heard about this process for the first time from Bingham in this way. But the great thing about cyanotypes is they don't require cyanogen to produce at all. It's just very, very strange to describe, for example, potassium ferrocyanide as a salt of iron in combination with cyanogen. Cyanogen really means the cyanide originator from cyano, cyanide, and gen, like genesis or gestation. Basically, it's the source of something. And for some compounds, this makes sense. Oxygen is the generator, the genesis, the gestation of oxides, oxygen. And indeed, many oxide compounds are created from elemental diatomic oxygen, O2. But while oxides are often prepared by reacting something with oxygen, cyanides are almost never prepared by reacting something with cyanogen. So this is a really wacky name. It's also cyanogen that is prepared from hydrogen cyanide, which is prepared from inorganic cyanide salts. So really, cyanogen is at the end of the synthetic pathway rather than at the beginning, despite the gen in its name, like Genesis. You can think of there being 4 general categories of cyanide compounds that are grouped by ease of handling. At the top, you have compounds where cyanide is either an ion that's tightly bound, as in potassium ferrocyanide right here, or in some stable organic compounds, such as with nitrile rubber. Nitriles are really just organic cyanides. These compounds are great to handle because when the cyanide is tightly complexed or stably organically bound, that abolishes its toxicity, or at least it greatly reduces it. Then you kind of have the upper middle level. You have the alkali metal cyanides. This is your potassium cyanide, sodium cyanide, these sorts of reagents. Really, these are the bread and butter of cyanide chemistry. In these cases, the counterion doesn't bond the cyanide ion tightly, so they're fairly toxic, but they are at least solid. They're non-volatile, they're non-flammable, and they're non-explosive, so they're pretty reasonable to handle. They're also generally not too hygroscopic, so they're easy to weigh and measure out. Kind of another rung down the ladder, you have hydrogen cyanide. It's highly toxic, very volatile, and very flammable, but it has that hydrogen bonding, just like water, to kind of keep it either in solution or as a cryogenic liquid and to prevent it from boiling too quickly. And finally, at the very bottom of the ladder, you have cyanogen. And this description by Bingham leads you to believe that you need to work with cyanogen, which is the very worst of the cyanides. But in truth, you can just work with potassium ferrocyanide, which is the best of the best to work with. Bingham also writes that to make a cyanotype, quote, paper is washed over with a moderately strong solution of the ammonium citrate of iron. First of all, a moderately strong solution? Excuse me? What does that mean? I mean, ferric ammonium citrate is super soluble in water, so what concentration should you use? Should you just make a saturated solution and then, I don't know, take its concentration down by half and then use that? Can we at least get a suggested concentration, like 5% on a mass volume basis? I mean, if a patient comes in, he has epilepsy, you can't write him a prescription for a moderately strong dose of sodium valproate or something. A pharmacist is not going to fill that. He's going to call you up and he's going to ask, excuse me, like what dose do you want for this guy? How much should I give him? And sure, the pharmacist is going to have dispensed a lot of prescriptions for anticonvulsants, so he's going to have some idea. He's going to be familiar with the typical doses, but he's not going to just guess what you mean by moderately strong. If you're writing up a procedure for photography or anything else, you need to at least give an example of a concentration that works. You don't have to die on that hill. You don't have to say a 9.843% mass volume solution of ferric ammonium citrate is the ideal concentration for every possible substrate in every possible situation. You don't have to choose a hill to die on like that. But you should at least provide an example that works, some kind of guidance to help people reproduce it. Also, ammonium citrate of iron does not specify the oxidation state of this iron. Is it +3, as in ferric ammonium citrate, or +2, which would be ferrous ammonium citrate? Now, the correct answer is +3, ferric ammonium citrate, but again, you really need to specify this. There's also a reference to, quote, a saturated solution of the common ferroprussiate of potash. First of all, a saturated solution at what temperature? But more importantly, though, this is clearly a reference to some sort of iron potassium cyanide compound, the salt of prussic acid, that is, hydrogen cyanide or hydrocyanic acid. But the term ferro implies that this is potassium ferrocyanide with iron in the +2 oxidation state. And I'm fairly certain that this is a mistake, and the proper reagent should be potassium ferrocyanide, or one could say ferroprussiate of potash as opposed to ferroprussiate of potash. This is because if you expose paper containing ferric ammonium citrate, you'll get +2 ions in the exposed area and still have +3 ions in the unexposed area. And then if you dip such paper or cloth or whatever other substrate you're using in potassium ferrocyanide, you'll end up with Prussian blue in the unexposed areas rather than the exposed areas, which would mean a positive process instead of a negative process. And cyanotype is, as it exists today, an inherently negative process. Bingham writes that when this is done, quote, the negative picture vanishes and is replaced by a greenish-blue one with greenish-yellow ground. Does he mean that the negative vanishes and is replaced by a clearer negative, or does he mean that the negative vanishes and is replaced by positive? I'm fairly sure he means the former, but again, this isn't written clearly at all. I also doubt that making a positive cyanotype in this way would actually work, because even in the exposed areas, it's likely a negligible fraction of ferric ions that get reduced to ferrous ions. And to get good contrast, you need contrast between the unexposed areas with no ferrous ions and the exposed areas that are going to have some ferrous ions, rather than between the unexposed areas with lots of ferric ions and the exposed areas with slightly lower levels of ferric ions, but still presumably quite a few of them. There's also the fact that ferrous ions tend to get rapidly oxidized to ferric ions unless they're tightly complexed, at least in an oxidizing atmosphere such as the atmosphere on Earth, our lovely home. I've also read about so-called ferroprussiate paper. You can read about it in Sir Fredrick William Herschel's On the Action of the Rays of the Solar Spectrum on Vegetable Colors and on some new photographic processes, and this was entered into the records of the Royal Society of London on June 15, 1842. I'll put this document on screen as well. On page 22, Sir Herschel describes the ferrosesquicyanurate of potassium as being manufactured in abundance and purity by voltaic action on the common, or yellow, ferrocyanurate. In this process, nascent oxygen is absorbed, hydrogen given off, and the characters of the resulting compound, in respect of the oxide of iron, forming as it does Prussian blue with protosalts of that metal, but producing no precipitate with the persalts, indicate an excess of electronegative energy, a disposition to part with oxygen, or, which is the same thing, to absorb hydrogen in the presence of moisture, and thereby to return to its pristine state under circumstances of moderate solicitation, such as the affinity of protoxide of iron, for instance, for an additional dose of oxygen, etc. Since this ferrosesquicyanurate of potassium is being manufactured by electrochemical oxidation of yellow ferrocyanurate, and we know that potassium ferrocyanide, that is potassium iron 2 cyanide, is yellow, whereas potassium ferricyanide is, this reddish-orange color, we can assume that when Bingham is writing about ferroprussiate, he actually means ferriprussiate, potassium ferricyanide, or potassium iron 3 cyanide. I've also read through Humphrey Desmond Murray's 1935 patent for ferroprussiate printing. This is patent 2,014,692, and it gives me the same impression that Bingham is probably referring to potassium ferricyanide or ferroprussiate of potash, even though he says ferroprussiate of potash, which would be ferrocyanide. This patent is quite interesting, by the way. When Sir John Fredrick William Herschel invented the cyanotype process, he refused to patent it so that it could be for the benefit of all mankind, just as Louis Daguerre did for the daguerreotype, and just as Alexander Fleming refused to patent penicillin. But this reservation really only applied to Britain, and so Humphrey Desmond Murray, despite also being an Englishman, kind of went behind Sir John Frederick William Herschel's back and patented cyanotype printing in the United States. I mean, what a jackass doing something like that. The patent expired a century ago, though, nearly, so you don't have to worry about the ghost of this ass clown, coming back and trying to shake you down for royalties or something. Aside from mixing up potassium ferrocyanide and potassium ferricyanide, Bingham also describes a sort of hybrid of cyanotypes in conventional silver salt-based photography, and in this he calls for the use of a solution of nitrate of silver, specific gravity 1.200. He doesn't give the temperature for this, which is an issue, but more importantly, who gives instructions for making aqueous solutions in terms of specific gravity? I mean, sure, you can make a solution to a specified density if you have a hydrometer handy and plenty of time on your hands as well, but it's just much easier to make solutions to specified strengths according to mass volume percentage. So giving instructions in this way is going to cause a great deal of frustration for anyone trying to follow the procedure. Usually when you are using a hydrometer, it's to measure the density of a solution of unknown concentration, but hopefully of known solute, and then you can look up a table of densities, at least if there's one available for your solute and solvent, and get some estimate of concentration. But we very rarely make solutions to specific gravity as an endpoint, so this is another baffling aspect of Bingham's write-up. I'm going to try to do much better myself in terms of describing the cyanotype procedure. Here is the reaction scheme for the classic cyanotype, the Herschel process, as well as I've been able to work it out. My apologies. If this is difficult to read, you can download these materials from freeworldblues.com at your leisure and view them in higher resolution. You can scroll around as well. I've marked the light-sensitive reactants and reaction step in blue. The classic process uses citric acid in the form of ferric ammonium citrate as the photosensitive reductant. The overall approach is this. We prepare ammonium citrate, triammonium citrate from ammonia solution in citric acid, producing a triply deprotonated citrate salt. We then complex this with a solution of ferric chloride to form ferric ammonium citrate. This has iron in the +3 oxidation state, and notably, once the iron is present, we deprotonate the hydroxyl group of citric acid as well, effectively making it a tetraprotic acid overall, even though it's only a tricarboxylic acid. The reaction also produces ammonium chloride, but that's fine. The salt can stay dissolved and it will spectate the remainder of the reaction. We mix this ferric ammonium citrate with potassium ferricyanide, another compound of iron in the +3 oxidation state. Potassium ferrocyanide has the cyanide ions interacting with the ferric ions of the carbon side of each ion. Then we applied this sensitizing solution to a substrate, optionally letting it dry. This isn't strictly necessary, but certainly if you want to store your substrate, you should store it dry, and handling it dry will just reduce the mess it can create and keep it from contaminating any negatives you're printing from. Next, we expose the substrate to light, either printing from a photographic negative via the contact process, or making a photogram by placing objects on the cyanotype substrate directly, or by some other method. What matters the most is that in the areas where light strikes the substrate, the citrate will reduce the iron +3 to iron +2, converting the ferric ions into ferrous ions, and in this process it gets oxidized to acetone, dicarboxylate, and carbon dioxide. These ferrous ions then induce the cyanide ligands bound to ferric ions to flip around. In potassium ferrocyanide, the cyanide ligand coordinates iron on the carbon end, but because the carbon end of the ligand is a comparatively soft base, whereas the nitrogen end is comparatively hard, when we introduce a mixture of iron 2 ions and iron 3 ions, the cyanide ligands will bind iron 2 on the carbon end and iron 3 on the nitrogen end. This is what we would expect from hard-soft ligand theory, or hard-soft acid-base theory. The harder ferric ions bind cyanide at the harder nitrogen end, and the softer ferrous ions bind cyanide at the softer carbon end. This tendency produces Prussian blue as an insoluble, high molecular weight polymer, which forms the pigment that ultimately makes up the cyanotype. We can then simply wash the substrate, removing the remaining chemicals, all of which are quite water-soluble, except for the Prussian blue, which will stay in the paper or other substrate and produce our negative image. The new cyanotype, also called the fast cyanotype or blue flash due to its greater sensitivity, was invented by Michael Ware in 1994. Ware is an Oxford-educated chemist and a fellow of the Royal Society of Chemistry, so it's always those British and their cyanotypes, it seems. His book on cyanotypes, the Cyanomicon, is by far the best resource on the process available at over 400 pages. It's not only the most detailed resource available, but in my judgment, probably contains more useful information than all other resources combined, at least for English, Russian, and French language resources. I can't read any other languages, so maybe there's something even better written in Swahili. I think that's probably unlikely, but I can't rule it out, and certainly if there is, I'm sure some native Swahili speaker will yell at me for saying this. You can get the Cyanomicon from Ware's website for free, mikeware.co.uk, and I'll put a link on screen. The first edition was from '94, then the second edition came out in 2006, and I'll reference here the third edition revised in 2020. It's absolutely a breath of fresh air to be reading this, especially after slogging through Bingham's sloppy writing about Herschel's original cyanotype process. The key difference is that in Ware's process, the reducing carboxylate salt is oxalate, as opposed to citrate, and the byproduct of that reduction is simply carbon dioxide, as opposed to the citrate reduction producing a mixture of carbon dioxide and acetone dicarboxylate. Here's the reaction scheme again, as far as I've been able to determine it, and you can get a copy of this at freeworldblues.com. There are two main advantages of using oxalic acid, oxalate salts effectively, as opposed to citric acid or citrate salts. The first is that the oxalate-based cyanotype is much more sensitive to light, not quite an order of magnitude higher sensitivity, I would say, but close. I'll note that this sensitivity increase is related to higher quantum yield of the ferric to ferrous reduction by the wavelengths of light that work for both types of cyanotypes. So the Michael Ware variant, while it's more sensitive to blue light and UV, doesn't extend the sensitivity into longer, redder wavelengths of light. Both variants are quite orthochromatic, So what Ware has accomplished is making an orthochromatic process with a higher ISO, but not making an orthochromatic process panchromatic, which is, completely fine. The second advantage of the oxalate-based chemistry is that oxalic acid isn't as tasty to bacteria and fungi as citric acid. Oxalic acids and oxalate salts have some antimicrobial properties, and this has been known for hundreds of years, and the evolution of oxalic acid production in plants dates back millions of years. Despite that, it's not entirely clear why oxalic acid can harm microorganisms. It could be that it's strong enough to force protons onto carboxylic acid residues in proteins. So if you have a protein with lots of aspartic acid or glutamic acid residues, those are supposed to be negatively charged, but oxalic acid can force protons onto them and force them into the free acid form, which makes this section of the protein become lipophilic, even though it's supposed to be hydrophilic, and that could cause it to misfold and then not function properly. It could be that oxalic acid is chelating magnesium in a way that prevents magnesium-dependent enzymes, of which over 600 are known, from working as they should. Oxalic acid is also acidic enough that sometimes it can self-catalyze Fischer esterifications with alcohols. So it could be, cross-linking alcohol groups, and peptidoglycan or some important alcohol-bearing biological molecules. We don't really know why for sure oxalic acid can be so bothersome to microorganisms, but it is. It's also interesting that oxalic acid, even though it's usually thought of as toxic, is actually essential to living organisms, sort of like how since the 1990s, we've known that hydrogen sulfide and carbon monoxide and nitric oxide are actually essential to the body as gasotransmitters. But for whatever reason, the levels of oxalic acid or oxalate salts typically found in cyanotype sensitizer solutions used in the Michael Ware process are high enough to prevent most microorganisms from growing, whereas microbial growth is a common issue for the older citrate-based Herschel process because those microbes, they really like the citrus fruit flavored citric acid or citrate salts that are present in the sensitizer. Even though we're in the realm of inorganic chemistry, at least mainly, I think a retrosynthetic approach is useful to understand in cyanotypes. So let's start by looking at our destination. That's right, retrosynthesis is not just for organic chemists. Let's get acquainted with Prussian blue. Dawaj, poznakomimся, dawaj, poznakomimся. Now, if you look up the structure of Prussian blue in a library or online, the overwhelming majority of structures that you see are incorrect. This has been my experience at the least. You'll see structures like this one from the Journal of Inorganic Chemistry, and I'll put the citations for all of these into the recording. Here, the iron atoms are all color-coded orange, regardless of the oxidation state, which is a bit confusing because this is a mixed valence complex, and the oxidation state really ought to be shown for each iron atom because it really matters in this case. But you can interpret this drawing as the iron atoms coordinated to the carbon end of cyanide, the dark gray spheres being ferrous with a charge of +2, and the iron atoms coordinated to the nitrogen end of cyanide, the split blue and red spheres being ferric with a charge of +3. This would imply that there are an equal number of ferrous and ferric ions in the minimum unit cell, or that there's a 1-to-1 ratio of ferric to ferrous iron, which is wrong. The American Chemical Society featured Prussian blue in their Molecule of the Week, along with another wrong structure in absolutely horrendous resolution. I don't get why it's so bad, but it is. This isn't photography, this is digital rendering. You can render in any resolution that you might want. Are those GIF dithering artifacts on these atoms? Jesus Christ. And again, this is a putative Prussian blue structure from the National Institute of Allergy and Infectious Disease in the United States. They're part of the NIH. I'm not really sure why they're publishing unit cell diagrams of Prussian blue, but they are. They have a pretty wacky bunch of visualizations, though at least they've color-coded their iron atoms by oxidation state. I hate when people don't color-code their iron atoms by oxidation state. The ferrous ions are in orange and the ferric are in pink. This is a really wacky model. It looks like they used a mix of a space-filling model for the cyanide ligands and a ball and stick model for the iron ions. Someone really had a lot of fun messing around with the settings in whatever visualization program they're using, and I get it. These programs are often a lot of fun. So this is where your tax dollars are going, Americans, and my tax dollars too, producing unit cell diagrams of Prussian blue that incorrectly suggest a unity ratio between ferric and ferrous ions. This is outrageous. Wait until Doge hears about this. But on the plus side, they do have a cool visualization tool where you can spin this model around, you can zoom through it. It really is neat. It's Better than most AAA games made since 2010, I have to say. Oh, they even have a wireframe mode. These are some high polygon counts. We're entering Yandere dev territory here. It looks like the vision enhancement mode in MechWarrior 2. It looks like the Death Star. You can really have a lot of fun zooming around inside this incorrect Prussian blue unit cell, looking for the thermal exhaust port or whatever. Again, this is super cool, but completely wrong. Let's check in on the Germans. It never hurts to see what the Germans are up to. It's kind of something you should do from time to time, a bit like checking your smoke detector batteries, especially if you're a chemist. Let's look at their structures for Berliner Brau, or as the Austrians call it, Brausches Blau. Austrians are like Germans, except more so. Austrians are in fact more German than Germans themselves. This may seem counterintuitive, but it's actually quite true in my experience. Well, at least the Germans have labeled their oxidation states. Kohlenstoff, carbon, coal stuff, that makes sense. The same in Russian. Uglerod from ugel, meaning coal, plus radit, which is, to give birth, or raditsia, to be born, literally to give birth to yourself. It's very poetic. I like it. The Germans call nitrogen Stickstoff, Ersticht, to kind of extinguish, so it's like extinguishing stuff. The Russians call it azot, from the Greek zoltikos, meaning life, plus a, or, without, sort of like aphobic would be fearless. So this means without life, azot, which I suppose makes sense. If you breathe nothing but nitrogen, you would die. Of course, that goes for any other pure gas other than oxygen. I'm not really sure that nitrogen is deserving of being called death gas, since it's as simple as asphyxiant, and there are certainly many gases which are orders of magnitude more dangerous. Then again, nitrogen is the most common gas you can asphyxiate from, at least on Earth, so perhaps it deserves the designation. But then again, that's a very Earth-centric viewpoint. Most of the matter in the universe, well, most of it is dark matter, but normal matter, which is so normal that it's actually the minority of all matter, but we're made of it, so we call it normal. Most normal matter is hydrogen with a little bit of helium, and those will both asphyxiate you as well, so I'm not sure. I'm kind of undecided on this. But back to the structure. The Germans have, yet again, shown a unit cell with a 1-to-1 ratio between Eisen 2 and Eisen 3. I would have expected more from them, quite honestly. As nice and tidy as these structures may look, they are all wrong. The actual unit formula of the hypothetical anhydride is Fe plus 3, 4, Fe plus 2, Cn6, 3. That is ferric 4, ferrous cyanide 6, 3. We know that the ratio between ferric and ferrous ions in Prussian blue is 4-3. Out of every 7 iron atoms, 4 of them are in the plus 3 oxidation state, but only 3 of them are in the plus 2 state. And we've actually known this for a long time. We've been synthesizing this stuff since the early 1700s. Even 3 centuries ago, we knew the ferric-ferrous ratio wasn't 1-to-1, even though 99% of the diagrams of Prussian blue imply that it is. I'm not sure why everyone keeps drawing them this way. It may be a form of cytogenesis, not cytogenesis. Cytogenesis is related to cell biology, but cytigenesis, cytigenesis, when someone says something wrong, usually by accident, and then it gets cited, and then those citations get cited, and then the citations that were cited themselves get cited, and sooner or later everyone is confidently wrong. If cytogenesis is how cells reproduce, cytigenesis or cytigenesis is how citations do. It might have to do with the fact that a 1-to-1 ratio is very convenient and makes things look very tidy. Maybe there's some autistic desire for compounds to have nice, tidy structures, and people are just projecting their twisted fantasies by drawing them this way. There are actually a lot of people projecting their twisted fantasies into drawing, I would say, especially on Discord. Another issue may be that the 4-to-3 ratio is close to 1-to-1, so people think they can get away with fudging things. I'm not really sure. To combat this issue when synthesizing Prussian blue, we're going to synthesize it in a way that lets us experimentally confirm the correct ratio. We're also going to synthesize it in a way that isn't dependent on light-driven reactions, since our goal is just to make some, and it will be convenient if we don't need to use ultraviolet to drive the process. We'll do this reaction by titration. The aqueous solubility of ferrous chloride tetrahydrate is extremely high. It's 685 grams per liter at 20 degrees Celsius. And potassium ferricyanide is also very water soluble at 464 grams per liter, again at 20 degrees Celsius. Since the ferrous chloride is more soluble, typically we put it into the burette because the volume there is more limited. But these reagents both have excellent solubility in water, which means we can do it the other way around. And in fact, I am going to do it the other way around because that will prove my point about stoichiometry better. Our titrant will be potassium ferricyanide solution, 20% on a mass volume basis. We'll prepare 20 milliliters of this solution, so we will need 0.2 times 20 milliliters means 4 grams. Now we'll place this into a volumetric test tube. These are quite well calibrated, I've found in general, and this will give us our measurement of 20 milliliters. I'll bring the volume most of the way up simply by pouring it in, and then I'll pipette the rest of the way. As you can see from the color of the solution, this potassium ferricyanide goes into solution quite easily. Now that we've gotten to the point where there is no, or at least minimal, visual precipitate present, we can take the solution all the way up to 20 milliliters more accurately via pipetting. There we go, that's 20 milliliters. Now that we have our titrant prepared, which is 4 grams of this potassium ferricyanide in 20 milliliters of water, I'll go ahead and add it to the burette. Always making sure, of course, that the stopcock is closed before doing so, a common mistake. We can see we've lost a tiny amount, about 0.8 of a milliliter. So I'll actually prepare some extra solution off camera and bring this up to the required 20 milliliters for titration. The molecular weight of potassium ferricyanide is 329.24, so this 4 grams we've loaded into the burette is 0.01215 moles, and since it has 1 ferric ion per formula unit, we also have 0.01215 moles of ferric ions. Since we need only a 3 to 4 ratio of ferrous to ferric ions, we multiply by 3/4 to get a target of 0.009112 moles of ferrous ions, and that will be supplied by the same molar count of ferrous chloride tetrahydrate, since it also has 1 ion per formula unit. It has a molecular mass of 198.8012 grams per mole, so that means we need 1.81 grams. In theory, since the molar quantity is known, the amount of solvent for our titrant doesn't really matter, but I've chosen 200 milliliters as a convenient volume that I think will be easy to see. We're lucky that the 2 reactants we have here for this process are extremely water-soluble, and the product is virtually insoluble. If the solubilities were closer together, choosing the titrant volume would be a thornier issue, but fortunately, we don't have to deal with that. Now, I don't have a 200 milliliter volumetric flask or a 250, which is more common, but I still don't have one. So what I'm going to do is first make the ferrous chloride solution in 100 milliliters of water and then add another 100 milliliters into the beaker. Now, I know this is going to upset some people because you're not supposed to do this, I know someone's going to say, ahem, you're trying to make 200 milliliters of a 0.905 mass volume percent ferrous chloride solution. Don't you know that you can't just measure out your solute and throw in 200 milliliters of solvent? You're supposed to have a total volume of 200 milliliters. And while mass is conserved in chemical and physical reactions, including solvation, volume is not. Don't you know that if you mix 100 grams of ethanol and 100 grams of water, you'll always get 200 grams of solution? But if you mix 100 milliliters of ethanol and 100 milliliters of water, you'll only get 192 milliliters of solution, not 200 milliliters. You'll be 8 milliliters short because the density of a 50% solution of ethanol and water is not guaranteed to be equal to the weighted average of the densities of the two liquids, because there's hydrogen bonding that goes on between the hydroxide and the ethanol and the water molecules and blah, blah, blah. They do this, that, and the other thing. Why, someone's going to say, I work in a pharmaceutical company. I make insulin for a living. I would be fired if I made solutions the way you're doing right here. They'll say the proper way is to add solvent until you reach the target volume, not to start with the target volume of solvent and add it to the solute. Someone will say, oh, I work in a hospital pharmacy and I compound cyclophosphamide for the oncology department. All our solutions have to be accurately compounded to 4 decimal places. I could kill someone being as sloppy as you, blah, 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 blah. And you are right. This isn't the correct way to make a solution with volumetric flasks such as this, but since we do know the total mass of our titrand, the exact concentration isn't that important. We can be off by 1% and it won't be the end of the world, and it won't interfere with our ability to determine the stoichiometry of Prussian blue and hence confirm the ratio of ferric to ferrous ions. There we have our 1.81 grams of ferrous chloride tetrahydrate in a 100 milliliter volumetric flask, and I'll then take this up to 100 milliliters. I'll start doing so quickly by pouring from a beaker, and then do so slowly and carefully with a pipette. Now that all, or nearly all, of the visual solute has dissolved, I'll go up to the line with a pipette. That should do it. And now the moment of truth. Let's go ahead and start this reaction. Now that wasn't supposed to happen. As you can see, the drops are actually coming from the stopcock. That's a bit better. We can see the Prussian blue forming now. Now, despite this leaky stopcock that we had here, the solution that leaked out of the stopcock did at least fall into our titrand, so the titration should still be valid. You can see we started with a marking of 5 milliliters, and we've now used a portion of that. What I will proceed to do is titrate down to 1/4 remaining of the 20 milliliters of potassium ferrocyanide solution that we prepared, because if the ratio, the molar ratio in Prussian blue between ferrous and ferric ions is indeed 1:1, that would imply that we would only need 3/4 of the amount we expected that we would need of ferrous cyanide. So what I will do is now titrate down to that point at which we would expect the reaction would be completed if that 1:1 ratio were correct. As you can see, we've titrated from 5 milliliters down to 20 milliliters. So 5 minus 20 is -15, so we put 15 milliliters of the 20 milliliters of solution of potassium ferrocyanide in. And let me tighten this down, find a position that doesn't leak. That looks okay. I think that will be the last drop. And so now that we're in this state, we would expect the reaction would be completed if there were a 1:1 ratio. So what I'll do is I'll allow this Prussian blue to settle, which it does quite readily. It's extremely insoluble. And then we'll see if adding the additional last 25% produces a reaction. As it turns out, my Prussian blue was separating very slowly. This stuff can tend to form colloids, as you can see here. So it can take quite some time for it to precipitate out, and I let this stand overnight. Unfortunately, my burette didn't leak. I tightened down the stopcock here before I left it. I did keep a beaker under it overnight just in case, though, because I don't want potassium ferrocyanide solution dripping all over my table and making a huge mess. And I also was sure to cover everything temporarily with cling wrap so that we wouldn't have too much evaporation overnight. So just to recapitulate, we titrated it from a burette reading of 5 to a reading of 20 milliliters, which means that we've added 15 milliliters of our titrant. And since our titrant is 4 grams of potassium ferrocyanide at 329.24 grams per mole, that's 0.01215 moles, and we titrated 15/20ths of it, so 15/20ths, also known as 3/4, of 0.01215 is 0.00911 moles that we've added. That's 0.00911 moles of ferric ions, of iron plus 3 ions. And if you'll remember, our titrand that we have here in the lower beaker also contains 0.00911 moles of ferrous ions from ferrous chloride tetrahydrate. So we've achieved a 1-to-1 molar ratio of these ionization states, just like is shown in the vast majority of putative structures for Prussian blue that you'll see online and in libraries. So if the ratio really is 1-to-1, that means this reaction is finished. And if I open the stopcock, we should see no further reaction. I'll bring the camera in closer and we'll do exactly that and see what we find. Now I'll open the stopcock carefully and see what we observe. Still pretty tight. Loosen it a bit. It looks to me like we're seeing additional precipitation of our Prussian blue. What could that imply? Well, it could possibly imply that the ratio between ferric and ferrous ions is not actually 1-to-1. It's actually 3-to-4, which is indeed the case. So this is a demonstration of how titration can be used to determine the actual ratio of reactants, and in this case, the ratio of iron-ion oxidation states in this multivalent complex. We will prepare both cyanotype sensitizers from scratch, and I think we'll do them in the order in which they were invented. I strongly believe that in education, formal or otherwise, and most education is informal, the neophyte or the novichok should be introduced to technologies in the order in which they were created. Hence, when you're teaching a child mathematics, you start him out with no tools at all, save for his 10 fingers to assist in counting. Then you can give him maybe some pebbles to count with. The first counting devices in use were simply naturally occurring objects that were repurposed for that application. Then it's time for an abacus, the first purpose-built mathematical tool, at least in the old world. If you're going kind of more South American, more New World in terms of education style, then instead of an abacus, you can go with a quipu, basically a system for record keeping and calculation based upon tying knots in textiles and kind of strings and ropes and stuff. Then once the student is ready, you can introduce a 4-function calculator. You've got your addition, subtraction, multiplication, and division. And then as he continues to advance, you can provide him with more powerful tools such as a graphing calculator, a copy of Excel, and cutting-edge, desktop computer software. But you don't sit a 5-year-old down with a copy of Wolfram Mathematica. I mean, sure, Mathematica is an incredible tool, but you want to introduce technology in the order it was created, else you'll never cultivate within the student the basic skills which form the foundation for all else. I do actually have a soft spot for Mathematica. I recall back in 2006 when I was studying chemistry at university, I had a friend and lab partner, we'll call her ELHS, and she had given up an opportunity to fence for the United States Olympic team in order to attend university, which was probably a great choice. I mean, there's more money in chemistry, in industry, in medicine than there is, in fencing. But still, she was conscious of the sacrifice and a bit conflicted about it, which I think is really more than understandable. I didn't have to choose between university and a shot at an Olympic gold medal, so for me it was an easier choice than it was for her. And I think it's understandable that making a difficult choice is going to leave a man or a woman in this case with regrets, even if it was probably the correct choice. She was tiny ELHS, kind of a bit mousy, just platinum blonde. And I'm not really sure how that works for fencing. I'd imagine you'd want to be kind of tall and lanky for more reach when you're fencing, I suppose. But if you're small, then you're also a smaller target. And maybe she had long arms, for her height. I don't really notice or think about such things. Maybe there are height classes or arm length classes in the Olympics or something. I don't really know. Another potential advantage to being small, and perhaps this is part of the reason that ELHS was offered a spot on the U.S. Olympic fencing team. I mean, they don't, offer you a spot unless you're really good at fencing, would be signal propagation time. You may have noticed, and I've certainly noticed, that small creatures tend to be inherently extremely evasive. For example, even though you're presumably smarter than a bee, more intelligent than a bee, I mean, I haven't met you personally, so I wouldn't know. But this is my sort of gentleman's assumption, and please don't ruin it by saying something foolish. Even though you're presumably smarter than a bee, you can't easily, reach out your hand and just snatch a bee out of the air as it, flies by or something. If you want to reliably capture a bee, or just, really look at a bee up close, you need to either, sneak up on her while she's distracted, and usually while collecting nectar from a flower, or you need some sort of special tool, usually some kind of area of effect or weapon, such as, a bee smoker to smoke the bees, or a net to capture them in or something. You're not going to be able to reliably just, grab a bee out of the air with your hand. I've been thinking about bees a great deal recently. As soon as my son learned that bees make the honey that he enjoys with his morning pancakes, he naturally became very interested in them. And whenever he's, near a flower on a sunny summer's day, he's always, listening for them and looking out for them. And he likes to, really get right up close to them and take a look at them while they're conducting their flower-related activities. And sometimes he'll even try to pet them, especially, bumblebees, because they're quite fuzzy. So it's only natural to want to pet a fuzzy creature. He hasn't been stung by a bee yet, though it's only a matter of time at this point, but that's fine. I mean, I was similarly guilty of annoying bees when I was a child, and similarly, I got stung on quite a few occasions. It's the way of the world, and this same process of being young, of pushing the boundaries and learning firsthand about the consequences of pushing those boundaries is really a part of our human heritage all the way back to our life in Africa some 170,000 years ago. And being, stung by a bee is quite harmless and has significant educational value. When I got my current phone, I'll get it here, it's a Samsung Galaxy S24. It's fine. I remember being excited to test the camera features here. There's been quite a bit of controversy over Samsung phones and their camera features, especially because Samsung was caught faking pictures of the moon. In short, Samsung advertised how powerful the zoom feature, which I think is this camera, I'm not really sure. This one looks like it would have the zoom on it. They advertised, how powerful this was, and they encouraged people to, go out and take pictures of the moon, of Earth's moon, and I mean, that makes sense, I suppose. High-powered zooms are generally designed for photographing distant objects, and the moon certainly qualifies as a distant object, at least on human scales, so it would be a good way to test the, zoom feature on this phone. But it turns out Samsung had actually secretly loaded stock images of the moon into their, phone software. And presumably these were, very high quality images that were shot through an actual, telescope, so that when your phone detected that it was set to high zoom and it was pointed at something that looked like the moon, it would actually alter your, blurry, terrible moon picture and add in details from these preloaded stock images of the moon. Perhaps they also use GPS and accelerometers and attitude sensors to do this. They can determine where you are on Earth and, which way your phone is pointing and what time it is, and try to figure out if your phone is, pointed at the moon, if your camera is pointed at the moon based on that. And then if it is, they can activate their lunar trickery so that Samsung fanboys can challenge Apple users to test their respective cameras and make sure that Samsung will always come out on top just by, pasting in a photo of the moon taken with an actual telescope over, your blurry photo. You do have to hand it to Samsung, though. I mean, it's such a petty little conspiracy. Who would have come up with such an idea? I certainly wouldn't have. It really is something unique and I think special. I do like Samsung products all right, but the corporate leadership and marketing department just keeps doing foolish things, like this. They're always trying to throw shade on Apple and its iPhones, but every time they do, they just end up embarrassing themselves and putting themselves, in fact, in a worse situation than they would have been in if they hadn't done any of this kind of tomfoolery. The lunar conspiracy isn't the only time they've done this. They actually relentlessly mocked Apple for removing the 2 point or the 3.5 millimeter it would be headphone jack. But guess what? You see the bottom of my phone here, and also, the top of my phone and the sides of my phone and the back and the edges. There's no 3.5 millimeter headphone jack. So that's right. Samsung made fun of Apple for removing analog headphone jacks, and then they themselves removed analog headphone jacks. It's sort of as if two students were taking an exam. Samsung peeks over at Apple's exam paper, viciously mocks them for their wrong answers, and then proceeds to cheat by copying off those exact wrong answers, from Apple's exam paper anyway. This sort of thing just keeps happening. It won't seem to stop. Samsung just can't seem to resist the urge to shoot itself in the foot, and I'm sure that we haven't seen the last of this. Samsung also, I would say, can't seem to admit that the plus size variants of Samsung products, which are now really the Samsung Note products, are for plus size users. It's just a fact that the aspect ratio, the width to height ratio, or the width to height ratio of a Samsung phone is correlated with the aspect ratio of the user. I have never seen a thin man use a Samsung Plus product, and really I've never seen a woman of any weight use such a product. Samsung just needs to admit that their, wide ass oversized phones are for lard ass oversized men. That's just a fact. And I think it's time for Samsung to admit it. This could actually be, in the long run, a positive thing for the company because in the post-industrial revolution era, people are just, getting fatter and fatter. So if you make phones for plus size people, your audience of purchasers, your consumer base is growing, literally. In the case I'm talking about here, though, I wasn't using Samsung's, space zoom feature to take pictures of the moon or anything. I was actually using the high-speed camera feature, and my son was trying to pet a bee, a bumblebee, of course, the, fatter, fuzzier sort, and it flew off. And I could actually see in the video, that I shot with my phone, that it took off backwards. And in fact, bees have the full 6 degrees of, freedom in flight. They can fly sideways, they can fly upside down, they can fly backwards. They can even do all three at once if they really want to, if the situation calls for it. Of course, some orientations of flight are preferred. You generally want to, fly forwards because that's a more energy efficient orientation. And you also obviously want, good visibility in the direction you're moving. But this isn't strictly necessary. And in emergency situations, bees can fly, up or down, forwards or backwards, left or right, or any combination of these, while simultaneously they can roll, they can pitch, they can yaw, and they can do any of these things in any combination. They can also, roll and pitch and yaw about an arbitrary axis, not just the axis of their physical body. But it's not just this that makes bees very evasive, it's also their small size, at least, in comparison to humans. Neural conduction velocities will vary between organisms and nerve types, but very generally they're on the order of 100 meters per second. That's around 360 kilometers an hour, or 230 to between 220 to 30 miles per hour. So no matter how quickly you can get nerves to conduct, even if you could, push the conduction velocity up to the speed of light, to really the speed of causality, which is, of course, the hard upper limit, a shorter nerve or cable is always going to mean a shorter signal transfer time, all else being equal. And a human is about 2 meters head to toe, although I'm quite a bit shorter than that. And a bumblebee is about 20 millimeters long head to its, fuzzy rear end there, so around 100 times smaller in a linear sense. Obviously, when a man tries to, go and snatch a bee out of the air, the distance from his brain to his hand isn't going to be, the full 2 meters. And when a bee, flies about the distance from her brain to her, wing muscles isn't going to be the full 20 millimeters, but the ratios should still hold approximately, I think. So let's suppose that the muscles which, actuate your fingers here are about a meter from your brain, half of your length. And let's say the muscles that activate, a bee's flight muscles are a centimeter from her brain, half her length. If nerve signals travel at 100 meters per second, then when you see a bee, kind of about to be in your grasp and your brain signals to your muscles to, close your hand, the delay will be approximately 10,000 microseconds. Meanwhile, when the bee is, seeing your hand about to, close and envelop her, the nerve signals from her brain to her flight muscles have a delay of only 100 microseconds. This means that every time you have an opportunity to make just one single, course correction as you're moving your hand around pursuing this bee, she can make 100 different course corrections to try to evade you. And it's like if you're playing chess, if you're playing a chess game and your opponent gets to make 100 moves every time you can make only one move, you're going to have a very difficult time winning that chess game. You're almost certainly going to lose. And it's the same situation with bees and flies and dragonflies and, wasps like yellow jackets and mosquitoes and butterflies and moths and such. Just trying to snatch them out of the air with your hands is an almost hopeless prospect. It's about the same with small fish, which can, in their own sense, fly around in an ocean of water, just as birds and insects and bats can fly in this ocean of air that we all, live at the bottom of. I enjoy diving and I also enjoy seafood. And the thing is, I'm very susceptible to nausea from all causes, including nitrogen narcosis. And of course, diving, I'm careful to avoid depths and gas mixtures that could cause narcosis. But as an added precaution, I generally fast before diving, just as you would before a planned surgery, because vomiting while using scuba equipment can be very dangerous. There are procedures and training protocols for vomiting underwater, as well as, vomiting if you're using any sort of supplied, breathing gas apparatus, which could be used for firefighting or certain kinds of industrial or laboratory work where there could be dangerous gases or, microbes present, or in the context of chemical weapons countermeasures. But I won't go into those vomiting procedures here. It's pretty unpleasant. But suffice to say that vomiting, while underwater, like during surgery, is very dangerous. There's a risk of, aspiration of vomitus, so it's something to be avoided. The only time I've ever been heavily narked was in a dry, dive, a chamber on air. And while many people seem to enjoy a bit of narcosis, it's compared to ethanol, but I would say it's more similar to the effects of nitrous oxide. The overwhelming effect that nitrogen narcosis had on me was just terrible, terrible nausea and, vomiting and retching, and that will ruin your experience real quick. They did fortunately have a trash can, in the chamber, so I could keep things pretty tidy, but still it was a very unpleasant and memorable experience. I think there were 6 of us training in the chamber, plus 2 instructors, and the purpose was to demonstrate nitrogen narcosis in a safe environment, and it was because of my condition that the dive had to be aborted, and we were, the chamber was ascended gradually back up to ambient pressure. I'm sure it was quite a buzzkill to everyone who was, enjoying their nitrogen narcosis, especially because we were quite, cozy shoulder to shoulder in the chamber, but there was, nothing to be done about it other than to abort the chamber dive. This is just my physiology, and as a result, I fast before diving. But that fasting usually means I'm quite hungry when I'm underwater, and combine that with my love of seafood, and you'll understand why I'm tempted to grab at all the fish that are swimming by. I mean, imagine you haven't eaten in 24 hours. I don't even like sushi that much, but as they say, hunger is the best spice. And suddenly there's a bunch of, free sushi snacks all around you, and they're just, they're there for the taking. They're as fresh as can be. It's only human to see a little fish swimming by and, go for a grab. But as with small insects, small fish have short nerves and short signal propagation between their brains and their, swimming around muscles. So they're likewise very difficult to snatch out of the water barehanded. Perhaps this is why ELHS was such a good fencer while being rather tiny. Muhammad Ali said, "Float like a butterfly, sting like a bee," and perhaps, by being small, she did really have some of the advantages that a bee would have. Smaller size just means shorter nerves, which means shorter signal propagation times, which means, faster strikes and faster evasive action. Sting like a bee, I think it's an appropriate metaphor for fencing because isn't the foil, reminiscent of a bee stinger? Most of her success, I'm sure, was just plain hard work and practice. I don't want to imply anything else. At the same time, when a man has, or in this case, when a woman has, reached the very top of the competitive level of a sport, or really the top level of any activity, it's usually going to be some combination of nature and nurture. I could train all my life, you could train all your life. Neither of us is ever going to swim like Michael Phelps, in all likelihood. And neither of us is ever going to fence like, ELHS in all likelihood. I mean, you look at Reinhold Messner, he climbed Mount Everest without any supplemental oxygen. I mean, did he train? Yes, he trained. Did he, avoid smoking? Yes, he avoided smoking, which was, rare for European men at the time. Did he eat right? Did he exercise and study mountaineering and meticulously plan and practice? Yeah, he did all those things. But he was also just built different from most of us. Almost no one can tolerate an oxygen saturation in the low 60s. That just isn't compatible with life for the vast, vast, vast majority of people who have ever lived. But there are, kind of scattered among us, these special people who can push their bodies and push their minds far beyond normal limits. And ELHS was like this in terms of fencing, which was why she was offered a spot on the Olympic fencing team, although she did turn it down. But she did fence recreationally at university, and she had a set of foils and other equipment. And one night when I had been drinking with another friend, I'll call him JSPL, he and I decided to borrow her foils, and she had several of them, and we started playing about with them, which was certainly not something we should have been doing because we weren't wearing any helmets, any face shields or whatever you call those things, in fencing. And in one of our matches, my friend actually struck me with his foil at kind of the corner of my right eye, really at the bridge of my nose. And it was a forceful enough stabbing motion to give the foil quite a bit of bend, and it actually bruised the base of my nose quite badly. But fortunately, I was, I had my head turned in such a way that the thrust of the foil, went kind of like that against, my nose, not into my eye socket. And, he's not at fault. I could have just as easily done it to him. And Miss ELHS, she saw this and she just, we lowered our foils, my friend and I, and she just gathered them up and, put them away. And none of us spoke a word, but we all realized that if the foil had, gone into my eye, I could have, lost my eye or even been killed if it went into my brain. And I will never forget the look on her face at that moment, or, the bend I saw in the foil. I was kind of, looking down the length of it. But what I remember second most about her, besides that, is that in the following year, in 2007, she told me something about Wolfram Mathematica, which, I had never heard of before. She said that it could perform symbolic integration. And I thought, she must be kidding. She must be, pulling my leg. It must just be another package for approximations, numerical integration, numerical methods. I just thought, there's no way that this would be able to perform symbolic integration. But she sat me down, and the university had just bought a license for all the students, so I could use it. And I'll be damned, it really could perform symbolic integral calculus. And this was just mind-blowing to me at the time. I thought to myself, wow, we really are living in the future. Then again, I've always been easily amused. Not easily pleased, but easily amused. Those two are actually quite different. But I think just as Wolfram Mathematica is too modern of a tool to start with on a mathematical journey, and just as it's best to begin with the earlier invented tools, I think we'll begin our cyanotype journey with Sir John Fredrick William Herschel's citrate-based process. I've chosen to target a potential developed result of 10 grams of Prussian blue, and at 859.23 grams per mole, this is 0.011638 moles. Now, each mole of Prussian blue as the unit cell, really the hypothetical anhydrous unit cell, contains 4 moles of ferric ions and 3 moles of ferrous ions. Therefore, we need 0.046553 moles iron 3 and 0.034914 moles of iron 2 per 10 grams of Prussian blue that could be created in the exposed areas of our cyanotype. Our source of ferric ions will be this potassium ferrocyanide, which has a molecular weight of 329.24 grams a mole and provides 1 ferric ion per mole. We multiply this out by the 0.046553 moles needed and get 15.3271 grams of potassium ferrocyanide. Now, our ferric ammonium citrate, although it begins with ferric ions, will, after photoredox, also yield 1 mole of ferrous ions per 1 mole of complex. And at a molecular weight of 520.21 grams per mole, that means we need to multiply by 0.034914 moles and get a target mass of 18.1626 grams of our ferric ammonium citrate. Now, each mole of ferric ammonium citrate will require 1 mole of ferric chloride, which also supplies our ferric ion, and then 2 moles of triammonium citrate. Our 0.034914 moles of ferric chloride hexahydrate at a molecular weight of 270.30 grams per mole is 9.43725 grams. We multiply this 0.034914 moles by 2 to get 0.069828 moles of triammonium citrate, which at 243.21 grams per mole is 16.9829 grams. As we would expect from the name triammonium citrate, for every molecule of this that we want to prepare, we'll need 1 molecule of our citric acid and 3 of ammonia. So we'll need 0.069828 moles of citric acid monohydrate, which is this stuff, and at 210.14 grams per mole, that's 14.6737 grams. We also need 0.209484 moles of ammonia, and at 17.03 grams per mole, that's 3.5671 grams of ammonia on an anhydrous NH3 basis. Ostensibly, the concentration of aqueous ammonia that we'll be using is 25%, and that's on a mass volume basis. So in theory, we'll need 14.2701 milliliters of this solution to provide our 3.56751 grams of ammonia. In practice, ammonia solutions tend to lose concentration over time, so in reality, we'll do this via titration and monitoring of pH. So let's get started. My target is 14.6737 grams, and you can see this is limonaya kislata, or lemon acid, which is, I suppose, appropriate. Kislata limonaya pishivaya, edible citric acid, and it specifically says here that this is the monohydrate. I assume that all, commercially available citric acid, or at least citric acid in this form for cooking purposes or household purposes, is the monohydrate. But I bought this brand specifically because it says right there, monogidrat, monohydrate. That reads 14.790 grams, which will be the actual mass. I'll go ahead and put this into approximately 100 milliliters of water. The exact amount isn't critical. And I do have this set up for stirring if necessary, and some heating as well, but I don't really expect that will be necessary because this stuff is extremely soluble in water, and I've got some nice warm water here. And as we can see, that is now dissolved completely in just over 100 milliliters of total solution. The main reason to include, enough solution more than just minimal water is to moderate the heat that's generated when titrating with ammonia solution. Now, triammonium citrate will ostensibly have a pH of between 6.0, or probably around 6.4, 6.5 to 7.7. So it'll be a nearly neutral compound. And so what I'm going to do is load up my burette with some ostensibly 25% aqueous ammonia solution. And then I'll be using this universal indicator pH paper in order to titrate. What I'll do now is take an initial reading with a pH paper. This is before we've added any ammonia. And as you can see, we're quite acidic. I'd say that's most likely a pH of approximately 3. So certainly we'll need at least 10 milliliters of ammonia solution, so I'll begin adding it. And that will be 10. We'll mix this around and we'll see where we are after 10 milliliters has been added. Keep in mind, we should need a bit over 14. We can see we're still at an acidic pH, but we're probably closer to around 5, I would say. Yeah, probably 4 to 5. That's 12. That's a pH of around 6. Yeah, 5.5 to 6, I would say. Let's add another milliliter and go up to 13. That's 13 milliliters, and it looks like we're still around the same pH. I would like to get to around 7, to around neutral. That is 14, which is ostensibly our target. The solution is warming up a bit. Looks like we're still a bit acidic. So I think I'll go to 15 milliliters. Still a bit acidic. Let's go to 16. We're almost at neutral now. I want to go a bit beyond because the reality is that excess ammonia is volatile, whereas citric acid is not, at least not under normal conditions. And so when we dry this compound out to get our yield, if we have a little bit of extra ammonia, that's fine. That's 17 milliliters. I think we'll go to 18 milliliters. Let's go a little further to 21 milliliters. Actually, I think I'll go to 22. And finally, I think we're at true neutral, so we can stop there. Now it's time for us to dry out our triammonium citrate, or our ammonium citrate tribasic. So I'm going to switch on heating and transfer it into a larger beaker. I could stir this mechanically, but it's such a small volume, I don't think it's too likely to bump out of this. And this is my first time, in fact, using this particular hot plate, so I want to see how it performs with just heating at the moment. This stuff is extremely soluble in water, so we'll need to take the volume down quite low before it starts crashing out. And in fact, it may also start to melt. It melts at 180 degrees Celsius. We don't want to melt it because we could damage it if we overheat it. So what I think I'll do is intentionally leave a little volume of water behind. That will mean that we don't risk overheating it. We don't risk going, much over 100 C or whatever the boiling point increase of water is due to the presence of this solute. And then we'll simply, lose a little when we go and filter it out, but that's okay. We'll have plenty left to continue making the cyanotype sensitizer. Our triammonium citrate solution has now been reduced in volume to only a few tens of milliliters, I would guess around 10 or 15 milliliters. And at this point, I'm also observing a slowing in the boiling, which indicates that nearly all the water in solution has been driven off. So we can now allow this to cool and crystallize, and then we'll get our yield. I'm not going to attempt to accelerate the cooling in any way, partly because I think we'll grow better crystals if it's gradual, and also partly because I don't want to apply any thermal shock to my glassware. And so hopefully we'll see crystals begin to appear, and this will be our triammonium citrate. Did you see that? Did you see the time lapse? Well, if you watched it very carefully, you'll notice that absolutely nothing happened. And I wasn't successful in boiling down my aqueous solution of triammonium citrate to the point of inducing crystallization. And it's at this point concentrated enough that I'm starting to see some boiling point elevation, which implies that I'm probably getting close to the temperature where I could start to decompose the product if I heated much further. And I certainly wouldn't want that. This is a bit disappointing, especially since I was able to quite easily precipitate as the monohydrate my other polyammonium carboxylate, namely diammonium oxalate. I suppose the solubility of triammonium citrate as we have here is probably even higher, and that's because in addition to having 3 negatively charged carboxylate groups, whereas the oxalate, of course, only has 2 of those, we have a hydroxyl group on the central carbon atom here, so that can engage in hydrogen bonding with water and increases the solubility. At the same time, though, this oxalate does have a lower molecular weight, which could argue for greater solubility of ammonium oxalates as opposed to citrates, but that's not what I'm seeing experimentally. This triammonium oxalate is being very stubborn, very disagreeable, and refusing to precipitate out of an aqueous solution. That's really the situation we're in right now. Now, one option, and I'll admit it is a tempting one, is just to proceed to the next step, the preparation of ferric ammonium citrate in solution. After all, that reaction is slated to take place in water as well, so we could just run this as a one-pot synthesis without needing to isolate our intermediate. But I do want to get a measure of our yield, and I think, just as importantly, this triammonium citrate has really offended me a bit by refusing to precipitate out of solution, so I won't be giving up on obtaining the anhydride that easily. I'll be making a second attempt at forcing crystallization by using isopropanol, also called 2-propanol. This substance forms an azeotrope with water, as many relatively short alcohols do. Now, you're probably used to thinking of azeotropes as a bad thing, and in many cases they are, or certainly can be. It's because of azeotropes that we can't fully separate ethanol and water with simple distillation. You can't, at atmospheric pressure, concentrate ethanol beyond around 95.6% by mass, because once you hit 78.2 Celsius, you get constant composition mixture that is 95.6% ethanol and 4.4% water. I remember when I was first learning chemistry and hearing about this back in 2001, I was quite surprised. I thought to myself, well, ethanol boils at 78.4 Celsius and water boils at 100 Celsius. So if you heat a mixture to anywhere between 78.4 and 100 degrees, all the ethanol will boil away into the gas phase and all the water will stay liquid. In fact, I thought to myself, well, if a liquid is heated above 78.4 Celsius at atmospheric pressure, it must contain, by definition, 0 ethanol, because all the ethanol would have boiled off by then. But this is not what we see happening empirically. You would think, perhaps, that because of Raoult's law, for any liquid mixture to be at equilibrium at a given temperature, the vapor that's located above must have a vapor pressure of each component that matches the vapor pressure of the liquid phase. So basically, the partial pressure in the gas phase must match the vapor pressure in the liquid phase for every component, but that's not actually so. The mechanisms by which azeotropes form are very diverse and they're incredibly complicated. And it's actually still quite an active field of research. But in short, when we have a mixture of substances, for example, in the liquid phase here, interactions between them can alter the chemical activity of each, resulting in a violation of Raoult's law. In the case of short-chain alcohols like isopropanol and water or ethanol in water, we typically see positive azeotropes or minimum boiling azeotropes, where the azeotropic mixture boils at a lower temperature than any of its constituents. There are also negative azeotropes or maximum boiling azeotropes, where the azeotropic mixture boils at a higher temperature than any of its constituents. And this is common for strong acids in water, for example, sulfuric acid, hydrochloric acid, nitric acid. Really, most commercially important strong mineral acids are like this. There are also even double azeotropes, where for a mixture of two liquids, there are two special azeotropic ratios, one of which boils above the temperature of the least volatile constituent, and one of which boils below the temperature of the most volatile constituent. And this is only for azeotropes of two liquids. There are also azeotropes of three or more liquids, and there's really no upper limit on how complex the behavior of an azeotrope can be or how many constituents it can have. Because of this, azeotropes are often thought of as an annoyance, and they certainly can be, both because they can exhibit quite intricate and counterintuitive behavior, and also because they pose actual problems for separating substances. The ethanol water case is an example. Ethanol can be used as a fuel, but it's desirable for it to be nearly anhydrous, since the water that's present in the azeotrope is capable of causing rusting and just general corrosion in fuel systems. But of course, you can't get anhydrous ethanol from normal distillation. You need to break the azeotrope with some co-solvent, and that typical co-solvent used in the normal approach is usually benzene or toluene. But these are aromatic substances which you usually don't want ending up in your fuel. They're more valuable as chemical feedstocks than they are as chemical fuels, so we try to extract them rather than just wastefully burning them in a gasoline or diesel engine or whatnot. And they're also among the most toxic constituents in petroleum fuels, and because of the strong bonds involved intramolecularly in the aromaticity, they also have less calorific value than aliphatic hydrocarbons. And beyond that, they are known to be the main, psychoactive constituents in gasoline, which could inspire some suspicious person to siphon off your gas and huff it.
We put the leaders over the islands. You don't save petrol from a can. You put the petrol in the high space. Don't be rama-ramas messing with your brain. You say you're deadly. Do you understand? You don't save petrol from a can. You put the petrol in the corridors. Don't be rama-ramas sniffing up your nose.
So we want the aromatics out of fuels. Fuel without them is cheaper, it will have better performance, and it's less attractive to these ne'er-do-wells. But when we break the ethanol water azeotrope with benzene or toluene as an entraining agent, we're going to end up contaminating our ethanol with traces of these aromatics, which is exactly the opposite of what you want for use in a fuel. And it's also not ideal if the ethanol is going to be used as a solvent or pharmaceutical feedstock or something, since one of the advantages of ethanol is its low toxicity. But once there's benzene in it, that advantage is, of course, gone. I'm going to add a little more water here to tamper down the boiling. Now, this is all very true, and as a result, azeotropes get a bad rap. People are like, down with azeotropes. I wish we lived in an azeotropic universe, a universe without them. But it turns out we can also exploit them to our advantage, and that's what I'll be attempting to do here. Isopropanol is miscible with water, but our triammonium citrate, currently in solution, is very insoluble in isopropanol because the triammonium citrate is just so polar. And isopropanol is pretty nonpolar as alcohols go. It's just barely miscible with water, and if you make water a bit more polar by dissolving sodium chloride or really most ionic salts, you'll actually break the miscibility. So isopropanol should act as an anti-solvent or counter-solvent here, dropping the solubility of triammonium citrate dramatically. But there actually is a second mechanism. If we look at the liquid-vapor equilibrium chart for isopropanol and water, we can see that the azeotrope is at 67.5% isopropanol and 32.5% water by molarity, forming a minimum boiling mixture at 80.3 degrees Celsius. This is below the boiling point of pure isopropanol at 82.6 degrees, and it's obviously also below the boiling point of water at 100 degrees. This implies that if we raise the concentration of isopropanol above 67.5% in this solution on a molar basis, then when we heat it, we will actually preferentially boil away our water and not our isopropanol, despite water being less volatile than isopropanol. Specifically, based on the ratios at the azeotrope, for every 2.07 moles of isopropanol that we boil off, we'll also remove 1 mole of water. So that's right. We are going to run a distillation where we preferentially boil off the higher boiling constituent. This is very strange, at least it appears very strange to me, but the math works, so I think we'll try it. I'll also note that key to this process is the availability of isopropanol, which is above the azeotropic mixture concentration. We need to enrich our solution beyond the azeotropic ratio for isopropanol, which of course would be impossible if the isopropanol we were adding was already at the azeotropic concentration. But fortunately, isopropanol is mainly made from petroleum. I think it's made from propylene or propene or something. Maybe they make it from ethylene and carbon monoxide or something like that. But they make it in a water-free petrochemical process. So this isopropanol, or absolutирование isopropylový spirit, is 99,7%, or 99.7% pure, which is far above the azeotropic concentration. So let's get started. I'm going to start by pouring a portion of my 99.7% isopropanol into a dedicated beaker and then putting this away because this stuff isn't, too flammable. It's certainly not as bad as something like diethyl ether, but you do want to be careful. You don't want to have a liter bottle of solvent on the table just kind of in front of you generally, especially around a hot plate, because there could be, an electrical source of ignition. I'm going to bring the camera in and we'll see what happens as we add this isopropanol to our nice and toasty solution of triammonium citrate in water. So here we go. You can see there's no presence here of any sort of crystals, but I'll attempt to crystallize this by adding some isopropanol. And I'm going to do this quite slowly and carefully because this is, of course, above the boiling point of isopropanol, above the boiling point of the azeotrope, and, even above the boiling point of water. So we want to be cautious as we add this because we may get a bit of aggressive boiling. So far, not too bad. One very interesting thing that I'm observing on the surface of the liquid, particularly as I just add the isopropanol, is actually some separation of phases where there are these hydrophobic droplets of isopropanol that are just kind of sitting on top of the solution until I stir it a bit. And that's because we're seeing a breakdown of the miscibility between the two liquids, water and isopropanol, because of the presence of the triammonium citrate. So our solute is actually causing there to be a bit of insolubility or solubility limitation between these two liquids, which are normally completely miscible. So it's performing a role similar to that of sodium chloride that you might use in salting out to try to separate these. And as I add more isopropanol, I can see a definite and marked split between the two. You can see that right there. There is indeed an interface between these two liquids, which are being rendered mutually immiscible by the presence of our triammonium citrate. That isn't particularly desirable at the moment, I would say, because I want them to mix together so that we can start disproportionately boiling off the water. So I'll add a bit more isopropanol. As I add more isopropanol, you can see there's a cloudiness beginning to form as more droplets of water get entrained into it. And that's also a result of the majority solvent switching over from water to isopropanol. So what we have here is certainly a two-phase solution. At this point, I feel somewhat comfortable adding our isopropanol here a bit more quickly. And now we simply wait as this rather anemic hot plate starts to boil off the water along with our isopropanol in the azeotrope. I've decided that I will add a stir bar to this mixture, hopefully get better mixing between our aqueous layer and our separated isopropanol layer on top. And I'll record this and you'll be able to see a time lapse of the process by which we remove the water. Now that we've gotten the volume of the solution down a bit, I can turn up the stirring here, and that will hopefully help to mix together the emulsion of our triammonium citrate in water with our isopropanol, and that should help it evaporate further, and hopefully we'll start to see some precipitation soon. Thus far, I've been rather unsuccessful in getting the water content down to the point where the triammonium citrate starts precipitating, so I think I'll add a bit more isopropanol in an attempt to draw off the remaining water. I'm going to try adding now 100 milliliters of isopropanol approximately, as measured out in this flask, in an attempt to get this emulsion to break up and form a true solution of water and isopropanol. Something interesting I'm noticing about this emulsion is that it's actually quite sticky. You can see it here, dripping off the end of this glass rod, so I believe that would explain much of why we're having difficulty getting this to mechanically stir, because this stuff has so much of that triammonium citrate in it that it's just becoming kind of syrupy almost. Well, that did not work either. It's rather unfortunate. I now have this sticky solution of triammonium citrate in water at the bottom of this beaker with a layer of isopropanol on top of it, and the polarizing effect of the triammonium citrate on the aqueous layer looks to have prevented me from utilizing the isopropanol water azeotrope to get rid of the water, and since the aqueous layer is so sticky and gel-like, I can't really stir it at slow speeds because the stir bar, if I try to do that, will just end up jamming. So I have to stir it either quickly or, I have to stir it either quickly or not at all, which means the stirring has basically beaten this into some sort of gel-like two-layered emulsion. Right. The correct next step would probably be rotary evaporation under a vacuum, but since I don't have a rotovap, at least not yet, we'll continue the synthesis, keeping the triammonium citrate in solution. As for the isopropanol, it likely contains, very little of the triammonium citrate. And so for that reason, I think we'll be able to get rid of it just with a, regular separatory funnel approach later, and then we can discard it. Now, the actual mass of citric acid that we added previously was 14.790 grams. If we divide that by 210.14 grams per mole for the monohydrate, that's 0.081327 moles, and we need half as many moles as that of our ferric chloride hexahydrates. That will be 0.40663 moles. At 270.30 grams a mole, that's 10.9913 grams of our ferric chloride hydrate, hexahydrate. So let's make an aqueous solution, and then we can go ahead and add it in. Here's my железо трихлорид шестводный. I think that's close enough. 10.895 grams. Okay, I'll add approximately 100 milliliters of water. We may have some water here for use as a recrystallization solvent. Now, conveniently, I do have this hot plate, and it is currently, as you can see, hot. Still heating that isopropanol and water solution of basic ammonium citrate, and so I can use that to help get this ferric chloride into solution. And really, very gentle heating is all that it actually took. Now let's go ahead and produce our ferric ammonium citrate. At this point, the solution will become light sensitive, but it's not so light sensitive that I can't, I think, reasonably do this in room lighting. As we can see, there's a color change from brown to green. Look at that. Now I imagine the breakup of this kind of disgusting sloppy gel at the bottom, composed of tribasic ammonium citrate, was more related to the addition of more water from the solution of ferric chloride rather than the chloride itself. But in any case, it does appear. So we should be able to heat this and boil off both much of the water and much of the isopropanol as an azeotrope and see where that gets us. Since the sludge is broken up, I expect that this should be relatively easy to stir again, and so I'll apply stirring as well as heating. I'll just turn off the stirring for a moment so you can hear me better. We're currently boiling off the last approximately 100 milliliters of water and isopropanol solution from our ferric ammonium citrate. Now, all of this room is rather well lit. There is one positive saving grace, especially when stirring is engaged, which is that even though light does cause the reduction of the ferric ion to the ferrous ion in this ferric ammonium citrate, so it would generate ferrous ammonium citrate, iron 2 ammonium citrate rather than iron 3, what tends to happen is that oxygen from the atmosphere will actually oxidize that ferrous iron back up to ferric. And so there is a bit of a regenerating effect from oxygen in the atmosphere, which means that although there is photosensitivity of this compound before we add our potassium ferrocyanide, until that ferrous ion can really be effectively trapped by those cyanide ligands and thereby stabilized, it is sensitive to air, which means that we won't have to worry too much about a reduction of the iron because it will end up being reoxidized in solution just by the air that's present, and it gets entrained by the stirring motion. I think it's also worthwhile discussing a bit why this azeotrope forms and why it behaves in the way it does. And when you have a positive azeotrope, which somewhat counterintuitively means a lower boiling point than you would expect based upon the boiling point of either substance, the reason for that is there's disruption of the structure of the liquid. And in probably the 10,000th example I can think of why you shouldn't believe everything that you were taught in school. When I was in school, I remember being taught that solids, have long-range organization, and liquids don't have long-range, organization of their atoms or molecules, although they do have a fixed volume but no fixed shape. And then gases are the most disorganized; they have no, fixed volume or fixed shape, although they do have a fixed mass of a certain, quantity, effectively, or number of, molecules or atoms of gas. And that certainly is true to an extent. I mean, if you look at a crystalline solid, even if you look at a snowflake, I mean, a snowflake is pretty small. It's, maybe a milligram or so in weight, perhaps even less. It's, a millimeter, a few millimeters across. But a snowflake is a single crystal of water, specifically. I mean, it's ice 1H, which is the normal form of ice. There are, I think, around 18 other polymorphs of ice that are known to occur at different temperatures and pressures. But with ice 1H, you can really get quite long distance structure. And I mean, if you think about a snowflake, even though it's pretty small, I mean, there are, trillions and trillions of water molecules. So if you look at one side of a snowflake to another, that means that, the water molecules on the right side are aligned with the water molecules on the left side in this, hexagonal structure, even though they're, trillions and quadrillions of molecules away, which is quite remarkable. And really, the only limit to how large a crystalline solid can, form crystals is the amount of material you have to make up the crystal and, the size of the container that you have for it. And so some quite impressive crystals can form, like, calcium sulfate, gypsum, or selenite. I'll put some of that on screen. I'll put some images of that on screen. Confusingly, this selenite doesn't contain selenium, but that's a separate issue. And of course, there are solids where you don't have crystalline structure. I mean, glass is an example. It's an amorphous, solid. It doesn't have a long distance crystalline structure. But I think there's a lot of room between, the idea of having crystalline structure that, ranges for billions and trillions of molecules and still having some structure, even though it's not long distance. And the reality is that, especially in very polar liquids like water or, something like dimethylformamide, even though you don't have that, very long range structure, and in this case, long range might be millimeters of distance, you still do have a significant amount of structure. There still is some hexagonal packing that, has irregularities over long distances, but still, in a very localized area where you might have just a few thousand water molecules, there still can be a lot of structure and organization there. And that structure and organization reduces the volatility of the water because it presents an energy boundary that needs to be overcome to evaporate it. And so when you add isopropanol, because isopropanol only has, one hydroxyl group effectively, whereas water could be thought of as having, two hydroxyl groups per molecule, two OHs, you do disrupt that structure. And that's really the origin of the higher volatility of these positive or, boiling point depressing azeotropes. But in any case, I'll turn the strain back on. You can see I've labeled this. It's probably a bit hard to read. These kind of transition metal structures, and especially those with hypervalent cations, tend to be a bit hard to visualize because they're very 3D, but I'll show some 3D visualizations of them as well that I've made that I think will be a bit easier to understand. But I'll turn the stirring back on here so we can entrain some more air and oxidize any of that ferrous ion up. And we'll take the volume down until we hopefully start to see some precipitation here. At this point, we're seeing significant precipitation of our ferric ammonium citrate. So what I'm going to do now is remove the stir bar, and I sadly don't have a dedicated stir bar remover. So I'm using this screwdriver, which is sufficiently magnetized. I know some purists are probably going to be rather upset at me for doing this, but I have washed off the bit in hopes of not contaminating anything. And then I'll just use some water here to clean off the stir bar and hopefully get as much as possible of our nice green ferric ammonium citrate back into the beaker where we can evaporate the last bits of water. Then we'll be able to crystallize it out and get our yield. That's most of it. Now, not unexpectedly, the bit of water that I added to get the stir bar clean, or at least mostly clean, and get as much of the ferric ammonium citrate into the beaker as possible, has resulted in it redissolving because the volume of solvent increased. So what I'm doing now is continuing to heat it, boil off the remaining water, and once it reaches the point where I start to see some crystallization, I'm going to pour it off via this funnel right here into this tube. And then I'll bring the camera in closer and hopefully we'll see as the water cools, we'll start to see some formation of ferric ammonium citrate crystals in that. Rather unfortunately, it appears to me that the remaining solution is so dark that even if crystals have formed, we won't be able to see them, even though I've pushed up the exposure on this shot by one stop. So what I'm going to do, now that this is nice and cooled off, is dump off the remaining solution, and hopefully we'll at least see some crystals have formed. And we can see clearly that we do have those nice crystals of ferric ammonium citrate. So I'm going to continue heating this gently to drive off the remainder of the water, and then we'll collect the crystals and get our yield. The time has now come to filter off our ferric ammonium citrate, which I will be doing with the help of this funnel and just the typical glass rod and spatula technique. I've now dried my ferric ammonium citrate in an oven overnight at 80 Celsius with plenty of dry air, so it's time for us to get a measure on the yield. I expect the yield to be quite terrible, not on account of the failure of the synthesis itself, at least not primarily, but rather because of all the trouble I've run into in recrystallizing this stuff. So ironically, the largest detriment to the yield is almost certainly the fact that I tried to measure the yield in the first place. If I had just kept this stuff in solution, there would have been little issue, I think. And normally when cyanotype solutions are prepared, everything is just kept in solution. There's no intermediate isolation step used. Now I masked the filter paper that this is located on before filtering the crystals into it and got a mass of 491 milligrams. Since we used 14.790 grams or 0.081327 moles of citric acid, we would ideally get half as many or 0.040664 moles of ferric ammonium citrate, and at 520.31 grams a mole, that's 21.1576 grams. So let's see what we've got. Wait for my scale to start up. It has a rather long startup time for some reason. I imagine it's doing some kind of self-calibration. Now we can zero it to the watch glass here. We'll tear it to that. And place our filter paper on top of it. As you can see, some pieces of the filter paper broke off as well when I was trying to remove it from the funnel. 13.4, is that 7 or 1? 13.475 grams. So we got 13.475 grams, and that's of course with the mass of the filter paper. And we'll subtract from that the 0.491 grams, and that gives us 12.984 grams. We'll divide that by our 21.1576 expected, and we have a yield of 61.4%. Now, that's actually not as terrible as I expected, and again, I think the vast majority of the ferric ammonium citrate is just in the funnel in the bottom of this that didn't get dried off, and so on and so forth. So certainly, if I were to repeat this, I would either not try to isolate it as a dry substance at all. You'll certainly get better yield that way effectively, even though you're not going to know your yield, but it will certainly be better. The second thing I would do is if I was trying to recrystallize it, I would probably use ethanol rather than isopropanol as the counter solvent, because ethanol will maintain miscibility with water, even though you'll be in a situation where you have the polarity of the water increased by the stuff being dissolved into it. Before we continue and produce the final cyanotype sensitizer, there are two tests I'd like to run. And the first of these is a taste test, or gustatory analysis, gustoassay, you might say. When I was first researching ferric ammonium citrate, I noticed that it's a registered food ingredient according to the World Health Organization and has an international numbering system identifier of 381 or 381. I'll put a link on the screen along with a screenshot of the website so you can take a look at it. So you can see INS 381, and according to this, 0.8 of a milligram per kilogram of body weight should be tolerable. It's not too surprising to me that ferric ammonium citrate is used in foods, at least in terms of adding iron to them. There aren't really too many iron compounds, especially ferric compounds, that are both water-soluble and reasonably non-toxic. You could try with ferrous compounds, but they're also not great in terms of solubility and will also get oxidized to ferric compounds by oxygen that's present in the packaging and such in many cases. And that's why, surprisingly, elemental iron, just iron powder, is sometimes added to things like cereal. And again, this is just little bits of iron metal. Presumably it reacts with the hydrochloric acid in your stomach or something, and you get ferric chloride, but I'm not sure what the destiny of ingested iron powder is. Ferric oxide or rust is very insoluble in water, and it's the same thing with ferric hydroxide. You wouldn't want to give someone ferric chloride, something like this directly, since it's quite corrosive. So you can't use the chloride or the oxide or the hydroxide as your counterion. It's the same thing with carbonates. They're just not soluble enough. So what else is there? Well, obviously you don't want to be using nitrate or perchlorate or something as your counterion. These are great for solubility, but they're salts of oxidizing acids, nitric and perchloric acid respectively, and these will oxidize up the iron in your hemoglobin from ferrous to ferrit, causing methemoglobinemia, and this oxidized hemoglobin can't transport oxygen. Oh dear, that's not very good. So normally you'd go for a carboxylate potentially as a counterion, typically acetate, since acetic acid is so cheap and non-toxic. But most iron carboxylates have poor solubility in water, so you'd have issues with bioavailability. You could try ferric sulfate, but the thing is the ferric ion is somewhat oxidizing, and since the sulfate counterion is already fully oxidized, at least as fully oxidized as you're going to achieve under normal circumstances, if that ferric ion wants to gain an electron and become ferrous, it's going to oxidize something in your foodstuffs, which can spoil it. Especially with fats, it will cause it to become rancid. So here we enter our humble compound, ferric ammonium citrate. It's very water soluble, unlike ferric oxide, hydroxide, or carbonate, and indeed unlike most iron 3 carboxylates. It's relatively non-toxic, unlike ferric nitrate or perchlorate. And unlike ferric sulfate, the citrate ion can serve as this sort of sacrificial reductant. If the ferric to ferrous reduction occurs, then the tightly bound citrate will be oxidized to carbon dioxide and some salt of acetone dicarboxylic acid, and neither of these are particularly toxic or foul smelling, and the CO2 will just come right out. So this will protect the more important food molecules. It's like a sacrificial anode in a sense. This valiant ferric ammonium citrate will give up its electrons to protect your food. It's really very cute. So I've wondered for some time what this compound tastes like. It's really not every day you would get an opportunity to taste iron ions, so I think I'll give this a bit of a taste test. And since I have some kind of, hanging at the bottom of the funnel here, I think I'll use this rather than the dried quantity. This portion never fully dried, so it's not included in the yield calculation. It's effectively free. Place this in here, get some water. And you can see this distinct, kind of bluish-green color. So I'll give a bit of taste to this ferric ammonium citrate. So that's quite unpleasant. I wondered if it would taste a bit like blood, because I imagine that, you're tasting the iron ion when you taste blood, although it's ferrous rather than ferric, so I'm not sure if that's actually the case. I would say it does have a bit of a blood-like aftertaste, but really the, foretaste or the primary taste that you perceive is actually, it's not the citrate. You don't get any, acidity from that. And you don't really taste the iron much, but you definitely taste the ammonium ion. And I would say I'm sorry, that's a bit disgusting, but it's just like wine tasting when people taste wine and spit it out. If it's good enough for them, it's good enough for me. I would say that the ammonium ion, it does have a salty taste, a bit like the chloride ion. It's very short-lived, it does have a salty taste, a bit like the sodium ion in sodium chloride. It's not the worst tasting cation. Certainly potassium is very bad, and anything quaternary ammonium is terrible. But this isn't a quaternary ammonium. This is just an ammonium, a primary ammonium, effectively. So it tastes salty in a sense, like the sodium ion does, but the saltiness disappears very quickly in a way that's almost, kind of strange or creepy. Like, you get the sense of having ingested some, sodium chloride salt, but then the saltiness just kind of, vanishes and it becomes a bit bitter. But there is a sort of there's a sort of blood-like iron aftertaste. So I imagine that's, coming from the presence of the iron ion. Although I wonder if ferrous ions, which are, normally present in blood, and ferric ions taste that different. Maybe they taste the same, or maybe the reason this tasted a bit like blood is because some of the ferric ions have been, reduced to ferrous ions just by the lighting that's present in this place, in my filming area. Or possibly it's because, when you taste blood, a tiny bit of that ferrous is oxidized to ferric just because of, normal chemical reactions in the body. And maybe when you taste blood, you're actually tasting that tiny minority of ferric ions, and that's why it tastes similar to this. But it does have a taste that is somewhat similar to blood, but that's mainly an aftertaste, and that ammonium taste is predominant and quite unpleasant. One of the foodstuffs in which ferric ammonium citrate appears is iron brew, where both iron and brew are misspelled, as you can see here, IRN and BRU. I've never had this drink before. I always assumed it was some sort of beer since, well, it comes from Scotland and it has brew in its name, but I noticed a can in Azbuki of Kusa, so I simply had to buy it. It was in the non-alcoholic drinks section, so that's actually how I learned that it is not, in fact, alcoholic. It is a soft drink, soft in the sense of not containing ethanol. Now, I'm a bit suspicious of any food stuff where the names of ingredients and processes are egregiously misspelled. It usually means one of two things. One possibility is that it's made overseas in a non-Anglophone country, Scotland, for example, and the translation is shoddy. And if that's the case, one wonders if the manufacturer wasn't careful about getting the translation right. Maybe they weren't so careful about food safety either. If they're cutting corners on hiring a competent translator and using Google Translate or something, maybe they're cutting corners somewhere else. The second possibility, also not a good one, is that the manufacturer got into legal trouble for calling their product something that it is technically not, and they had to change the name, and they decided to use misspelling to continue misleading consumers while not technically crossing the line in terms of adulteration and mislabeling. An example from Gringolandia would be Cheese Whiz, with cheese spelled C-H-E-E-Z, because the product doesn't meet the legal standard for actually being cheese, C-H-E-E-S-E. This is an aerosol cheese product, basically cheese in a spray can, like silly string. Another example would be Fruit Loops, with fruit spelled F-R-O-O-T, because, again, it doesn't meet the legal standard for being called fruit, F-R-U-I-T. And I'm quite careful about what I put into my body, and I recommend that you be as well. So, when you see things like this, it makes me a bit apprehensive. But I'm willing to take the risk, so I'll pour out a bit of Iron Brew, BRU, and give it a taste for the first time. Now, it's quite remarkably orange, and one of the ingredients is actually quinine, so I think we can perform an experiment here to see if we get any fluorescence before I taste it. I'm kind of putting this off because, again, I don't want to put, kind of something strange or sketchy in my body, and certainly with a misspelling like this, it does make me apprehensive. I've had to turn the lights off for this because the fluorescence is quite faint, and also this isn't an ideal lamp to be using for indicating fluorescence because it's not filtered to visible light, but I do think I see a bit of fluorescence from the quinine that's present in this iron brew. I've also carefully hidden away my ferric ammonium citrate so it doesn't get damaged by this ultraviolet lamp. Certainly a very strange looking liquid. So without further ado, I'll give this iron brew a taste. It tastes quite orange flavored. It does taste fairly acidic, I would say. I don't taste the quinine too much, so it doesn't have that bitter kind of flavor of tonic water, but certainly something that I would also recommend using the catch and release approach with when giving it a taste. I brought the can in closer so we can see what this stuff is. You can see here. Brewed, misspelled in Scotland to a secret recipe since 1901. Not brewed, B-R-E-W-E-D, but B-R-U apostrophe D. That's never a good sign. Sugar and sweetener, ingredients, carbonated water, sugar, acid, citric acid, flavorings including caffeine, ammonium ferric citrate, that's our ferric ammonium citrate, and quinine. I wouldn't really call caffeine a flavoring, although it does taste bitter like most alkaloids do. And we can see here in Russian. Okay. Напиток безалкогольный, сильногазированный iron brew, объем 330 milliliters. A drink which is non-alcoholic and strongly carbonated or literally gasified iron brew, volume 330 milliliters. Состав газированная вода, carbonated water, сахар, sugar, regulator кислотности, regulator кислотности, лимонная кислота, so citric acid as an acidity regulator. And then the flavorings are caffeine, citrate железа ammonia, which is our ferric ammonium citrate, and quinine. I do apologize for drawing random scribbles on this, but it's rather awkward from behind the camera. So this is how this drink is described in both English and Russian. The second experiment we can perform with our ferric ammonium citrate, which we produced here, is in the realm of magnetochemistry. Magnetism is an incredibly fascinating topic, as in you could read probably kilometers of bookshelves on it, and you'd only really scratch the surface. And in this case, I'll be scratching the surface even less, I guess you could say, grazing the surface. Looking at the magnetic properties of materials which have no bulk electrical flow, that is, we're not talking about electromagnets or superconducting coils of some exotic material with 1,000,000 amps running through them, or a swirling toroid of plasma or something. There are three general types of magnetism. First of all materials are diamagnetic, meaning that they experience repulsion in a magnetic field. This is caused by the external field pushing on electrons and causing them to precess or wobble in their spins, somewhat like the Earth has a slight precession which affects the timing of equinoxes and such. And I'll demonstrate that. I guess I could demonstrate that with this flask and rod. I'll give this a spin. You can see now it's spinning straight, but I can also wobble it and kind of precess it, and you can feel some resistance as a result of that. I'll precess it a little more aggressively here. A lot of friction from that ground glass joint, so this is not a great demonstrator, but hopefully you get, at least some idea of what I'm trying to show here. And I know that doing this is going to be immensely upsetting to a certain subset of people who are going to say that, oh, you shouldn't represent electrons as spinning. Electrons don't really spin. They'll say that electrons, well, yes, they have a net inherent moment of angular momentum, but having a net inherent moment of angular momentum is not necessarily the same thing as spinning. And I get that, but the predominant use of nomenclature is to say that electrons spin. So, that's what I mean by electron spin. And in this case, it's an example of electrons behaving as if they, really are spinning. In any case, this precession or wobbling generates a magnetic field that repels the external field, so the material is repelled. It's generally a small effect, difficult to detect without specialized instruments, although again, there are exceptions, and superconducting materials can display very strong diamagnetism, enough to overcome gravity and levitate them even in a fairly weak magnetic field. When we say a material is diamagnetic, what we typically mean is that diamagnetism is the only magnetic interaction it has, or at the very least, it's the predominant interaction. So to be clear, everything that's made out of matter is diamagnetic, but when we say such and such is diamagnetic, we generally mean it's either only diamagnetic, that's what we usually mean, or that it's predominantly diamagnetic. There's another kind of magnetism known as paramagnetism, which exists in materials that have unpaired electrons. For these materials, when a magnetic field is introduced, the spins of the unpaired electrons will, flip as necessary to align in such a way as to produce their own magnetic field, which will be of the opposite polarity to the external field, and that will create a net attraction. This effect only comes from unpaired electrons, of course, because if an electron is, paired with another one in its orbital, the two electrons will always have opposite spin directions, and hence the paramagnetic effect will be canceled out. Importantly, the effect of paramagnetism is generally orders of magnitude stronger than diamagnetism, which is why a material with unpaired electrons will usually be attracted to an external magnetic field, even though in most cases the majority of any element's electrons will be deeper down and they'll be in shells where they are paired. The third type of magnetism worth mentioning is ferromagnetism, which occurs when large-scale alignment of electron spins occurs within a bulk material. Ferromagnetism induces alignment of magnetic domains, which is why, unlike diamagnetism or paramagnetism, ferromagnetic materials will remain magnetized, even when the external field is removed. This can be reversed, for example, if something happens to scramble their domains. That can happen if the material is heated or strongly shocked or something of that nature. Notably, even though it is called ferromagnetism, not everything containing iron is ferromagnetic. In fact, even though our ferric chloride, which we have right here, and ferric ammonium citrate, which we have right here, both contain iron, neither of them is, in fact, ferromagnetic. But I have a large magnet here, kind of kept it safely on this styrofoam. This magnet is made from neodymium, and it is ferromagnetic despite not actually containing iron, so it can be quite misleading. Ferromagnetism doesn't mean that it occurs only with iron, and in fact, this neodymium magnet is much more strongly ferromagnetic than iron, and neither does it mean that everything that does contain iron is ferromagnetic. Indeed, none of our iron-containing substances here are ferromagnetic. And interestingly, neither really is, well, this is very weakly so, but neither really is this stainless steel spatula, even though it's made out of, literal elemental iron primarily. For the next part of this demonstration, I'll be using these two little boats that I made out of styrofoam, and I used pasta for the masts and then just some tape and some post-it notes to make little flags for them, because it strikes me that every boat should have a flag. I just cut them out and made them as uniform as possible. I used these holders for 500 milliliter round bottom flasks as templates for this. You can see. And just cut them out, try to make them as uniform as possible, cutting them out of this piece of styrofoam. It's very frightening. What we'll do now is to load onto each of these boats a mass of a ferric compound that contains approximately 500 milligrams of ferric ions, as close as we can get to that. The mass of the ferric ion is 55.845 grams per mole, so that half a gram will be 0.008953 moles. Both our ferric chloride and our ferric ammonium citrate contain 1 mole of ferric ions per mole of compound, so we can just multiply this by their molecular weights and get the amounts that we need. For our ferric ammonium citrate, we will need 4.66 grams, and for our ferric chloride hexahydrate here, we will only need 2.42 grams, since it's proportionately more iron by weight. So let's measure out these quantities, let's load them onto our boats, and let's see what happens when we introduce an external magnetic field. .685, that's certainly close enough. 2.47, that's also close enough, I think. Now it's time for our race to begin. First, our ferric chloride. Place the boat here. And here's our little container of ferric chloride. This is on the boat. Also try to get this massive ferric chloride as close to the middle as possible. There we go. And our ferric ammonium citrate. This is a little heavier, but I think the boat will also be fine. Excellent, we haven't had any capsizing yet. Now let's see what will happen. I'll gently move both of these, the ferric chloride being closer to the camera and the ferric ammonium citrate being closer to me, to one side. My glass rod here. I think that's about even. Then I'll hold my magnet here and we'll see what happens. As you can see, the ferric chloride is significantly more strongly attracted to the magnetic field. Ooh, look at that. Where's the ferric ammonium citrate? Not so strongly attracted. A much more gradual movement. I mean, you can pull it away from the magnet, but it really follows it, especially when it's this close. Look at that. Okay, ferric chloride, you go away. Now let's try the same thing with our ferric ammonium citrate. Definitely some attraction, but not nearly as strong as the ferric chloride. So in short, while both of these are attracted to our magnet, the ferric chloride is much more strongly attracted than the ferric ammonium citrate. So What's the reason for this? Well, first of all, the ferric ion is inherently paramagnetic. Iron has an atomic number of 26, that is to say 26 each of protons and electrons in the neutral state. If you subtract 3 electrons for the ferric ion, you get 23. 26 minus 3 is 23, and 23 is, of course, an odd number, so you'll always have at least one unpaired electron, and hence at least some degree of paramagnetism. However, the degree of paramagnetism is dependent on how those valence electrons fill the d orbitals. Sorry, I'm just going to put this magnet away before I attract something to myself at high velocity. If you were asked to write out the electron configuration of ferric ions in Chemistry 101 or some kind of very basic course, you'd write it as 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. Now, in some sense, that is correct. There are 5 electrons in the outer d shell, but this simple configuration implies that all 5 of the available d orbitals are energetically equivalent. Now, if you could, somehow isolate a ferric ion somehow and just have it, floating around in space or in a vacuum chamber or something, then this would indeed be correct. Yes, it would be the case that the d orbitals will all be entirely degenerate in terms of energy levels. But in actual compounds, and these are, actual compounds, you can see them, the energy levels of these orbitals are going to be influenced by ligands. Chemistry doesn't happen in a vacuum, at least not usually. In the cases of both our ferric chloride, which we have here, and our ferric ammonium citrate, which is right here, the iron ion is in an octahedral complex, which means that rather than having these 5 pentuply degenerate d orbitals, we actually have 2 different sets of d orbitals in the third shell. The lower energy of these are the 3 triply degenerate T2G orbitals, which are the 3dxy, 3dxz, and 3dzy orbitals. And the upper energy pair of orbitals are the doubly degenerate EG orbitals, which are dz squared and dx squared minus y squared. So the question remains, why are the EG orbitals higher in energy than the T2G orbitals? Well, it all has to do with the coordination sphere. When we're in octahedral geometry with ferric ions, since the ferric ion is positively charged, our ligands are going to themselves be negatively charged. At least they are in their, in the regions where they interact with the ferric ion. This could be a formal negative charge that we would write out, as in the case of, chloride or carboxylates or cyanide. These are both compounds where the ligand has a formal negative charge. Or it could be an implied negative charge with, nothing that we would write, but carbon monoxide, basically the carbonyl ligand, would be an example of such a case. But in either case, when these ligands crowd around our ferric ion, their own electron clouds will start to repel the electron clouds of the iron ion itself. When we're in octahedral geometry, the 3dxy, 3dxz, and 3dzy orbitals, namely the T2G orbitals, do not point directly at the ligands, and therefore they don't impinge all that directly on the electron clouds of those ligands, and with less mutual repulsion, it will be comparatively easy or energetically favorable to put electrons into these 3 orbitals. But the upper energy orbitals, which are the dz squared and dx squared minus y squared, the EG orbitals point directly at the ligands, and therefore they'll have more repulsion, therefore there will be more energetic cost, you could say, to populating these orbitals. So the EG orbitals have higher energy than the T2G orbitals. So what? That's the case for both our ferric chloride and our ferric ammonium citrate. So what's the difference? And the difference comes from how much the energy levels differ, because moving an electron from T2G to EG is not the only thing that has energetic cost. There's also an energetic cost to putting an electron into an orbital that already has an electron in it. Of course, by the Pauli exclusion principle, these paired electrons will always adopt opposite spins, but that only cancels out any magnetic moment, any net magnetic moment they would have. It doesn't cancel out their electrostatic repulsion, so there is some increase in energy associated with that, associated with the repulsion that these electrons feel, and it's that repulsion which creates the cost of pairing, and this is known as the spin pairing energy. Now, the spin pairing energy for the ferric ion will be the same whether we're talking about ferric chloride or ferric ammonium citrate, but the energy split between the T2G and EG orbitals is not the same. In the case of ferric chloride, the chloride ions are relatively weak ligands. We can see that if we look at a spectrochemical series, which I'll put up on screen. Ferric chloride hydrates, and this is the hexahydrate, also have water molecules as ligands, and water is also a fairly weak ligand, although it is stronger than chloride. But overall, this means that for ferric chloride, the ligands don't interfere too much with the EG orbitals. Hence, the EG orbitals are only slightly higher in energy than the T2G orbitals. This energy split is, well, what we call delta sub O, with O meaning octahedral. In the case of ferric chloride, it's more energetically costly to pair two electrons together in the same energy level, with opposite spins, than to move electrons from T2G to EG. And so electrons, being naturally inclined to laziness, will fill the orbitals as I've shown on this little boat's mast here, as I've shown on this little boat's flag here. One electron each in each of the three T2G orbitals, and one electron in each of the EG orbitals. In the case of ferric ammonium citrate, things are a little bit different. These carboxylate ligands are much stronger in a spectrochemical sense. They impinge much more upon the EG orbitals, resulting in a large delta O, or octahedral splitting energy, meaning that it's energetically more favorable to pay the cost of pairing electrons than the cost of moving them up from T2G into EG. It's this difference in electron spin state that gives rise to these different magnetic properties. While both compounds are paramagnetic, the ferric chloride that we have here is high spin with 5 unpaired electrons, whereas the ferric ammonium citrate is low spin. It only has 1 unpaired electron. More unpaired electrons means stronger paramagnetism, which is why our ferric chloride boat was the winner of the race when it came to being attracted to a magnet. This connection we've seen between photography, the cyanotype process, and magnetism is really a great example, I think, of why chemistry is so interesting, because you do see all these connections. We've seen connections between this form of photography and botany and linguistics, both in English and in Russian, as we look at Oxalospiralis zinfandel, which gives us the name. Oxalic acid came from that genus. And so I think you really can see a lot of serendipity if you understand chemistry, and that's why I've always enjoyed studying it. I would say as well, I can see a connection between cyanotype photography and the insane clown posse, and that actually comes sort of indirectly through magnets, because many years ago, when I was a user of Reddit, which I somewhat hesitate to admit, certainly it's probably the most shameful thing about me, I would say, if I look at my history and the mistakes I've made in my life. But I once was a Redditard. This was many years ago, and my alma mater had sent me an email. It was just, a forum email where they essentially talk about all their latest projects and, why you should donate money to them after already taking on $200,000 in student loan debt, which is a hard sell, admittedly. But in any case, they sent an email that explained that they had done an experiment testing Juggalo makeup, Juggalo face paint, I suppose you would call it, to see how effective it was as computer vision, or CV dazzle, basically to see how effective it was at preventing computerized algorithms and artificial intelligence from performing facial recognition on you. And they found that this kind of very stark black and white face paint, by breaking up the features of the face, made it extremely difficult for computer vision systems to function. And I decided to create a meme out of this, which was based on the template of the weak SpongeBob and the strong SpongeBob, where I included the article and then made an analogy between the weak SpongeBob and ICP's knowledge of magnets. and the strong SpongeBob and their knowledge of computer vision. And this was just meant as a joke. It's based, of course, upon their magnets. How do they work? Reference. And I didn't consider this to be a slight against ICP. I mean, I'm not a huge fan of ICP, but, I'll listen to Jump Around or What is a Juggalo from time to time. But a number of people who saw this on Reddit, who were ICP fans, became extremely upset and, thought that by pointing out ICP's, comment about magnets, that I was insulting their intelligence or something. And they became extremely agitated, and just, hundreds and then thousands of people from the ICP subreddit started, dogpiling onto me and sending me death threats, and some of them found my email address and sent me more death threats. So it was really the first time that I felt, wow, this is, this is serious. I've really hit a wasp's nest on the internet. And so that is the connection, even still, between the Insane Clown Posse and cyanotypes. I know that some viewers of this recording may be accustomed to living under a rock and kind of sticking their heads in the sand about things, so I'm going to explain a little bit more about this meme that I created. First of all, Juggalos are either followers of the musical group Insane Clown Posse, or they're members of the Insane Clown Posse themselves, namely the two members being Joseph Bruce, known as Violent J, here he is, I'll put a photograph on screen, and Joseph Utzler, known within the group as Shaggy 2Dope, and I'll put a photograph of him up as well. Something you've likely noticed about these gentlemen is that they have this stark black and white face paint on. You've likely also noticed that these are rather rough around the edges looking individuals. They're, tattooed up, including on sites which are visible even when clothed, their hands, their arms, their neck, their face, although the Juggalo face paint does obscure some of their facial tattoos, and from what I know of them, they seem to be generally decent people. They grew up in abject poverty in the ghetto of Southwest Detroit. They've been involved in, some gang activity and violent crime in the past. But again, you need to understand that growing up in such an environment, these kind of activities can be necessary for survival. I, myself grew up in an environment of relative, abundance and safety where I didn't need to steal in order to eat or use violence to defend myself. But the reality is not everyone grew up that way, unfortunately. And we need to recognize that. People also change, and again, these two Josephs, Bruce and Utzler, seem to be generally decent men, but certainly still not the sort of men one wants to cross, and I certainly didn't intend to do so with my meme. I would describe ICP as having some parallels to Marilyn Manson. These three fellows are certainly unusual gentlemen. Their performances are very theatrical, one might even say a bit freakish. But if you hear them interviewed in real life, when they're not putting on a show, it's clear that they are in all cases reasonably sane, intelligent, sober, level-headed, articulate individuals. And if you listen to the interviews on the O'Reilly Factor, and Joseph Bruce and Joseph Utzler and Marilyn Manson all did these interviews, it's evident that they're far more intelligent than Bill O'Reilly and absolutely trounce him in every aspect of the debate. Maybe that's not saying much, but it's worth noting. The Insane Clown Posse, like Manson, have also been the subject of numerous moral panics. You know the line, "We must protect the children. These freaks are teaching our kids to shoot up their schools and worship Satan and be gay and torture animals and do drugs and become communists and join Al-Qaeda." All the usual criticisms that politicians sort of, throw at you just to see what sticks. I would say that Manson has been the subject of more moral panic overall than ICP has, but then again, the Insane Clown Posse sees its fans, the Juggalos, designated as a gang by the FBI, the Federal Bureau of Investigation in the U.S. I've looked up the FBI publications, and I'll put them on screen. They're publications of the U.S. government, so, they're public domain. There's no issue with this. The FBI report also has an absolutely amazing photograph of a juggalette. That would be a lady juggalo, which I'll reproduce here. This is from the ATF, the Bureau of Alcohol, Tobacco, and Firearms, which is sadly really not as much fun as it sounds like it would be. As absurd as this designation of the Juggalos as a gang is, the reality is that the FBI did make such a designation, and as such they've deployed various sorts of targeted surveillance against Juggalos, including when they protested against that very gang designation during the Juggalo March on Washington. That was 2017, 09, 16. That was during Donald Trump's first term as acting president. It's also worth noting that ICP fans generally, although not universally, have a negative view of Trump and the Republican Party. And I think that's, understandable since that party has been disproportionately, although certainly not solely, responsible for inciting moral panics in the United States, including against juggalos, and I think this was likely a factor. There's this whole discourse surrounding whether a juggalo can be conservative or whether a conservative can be a juggalo, but I'm not going to dive too deeply into that at the moment. In any case, the American surveillance state did discover that juggalo face paint interfered with their facial recognition systems, and articles started to come out shortly after this. Something else you need to understand is that one of ICP's most famous songs is Miracles. This is the 15th cut from their 2009 record Bang, Pow, Boom. And by far the most famous part is this section by Joseph Utzler, aka Shaggy 2 Dope, which I'll play for you now.
Fucking magnets, how do they work?
Fucking magnets, how do they work? Indeed, indeed. For the last 16 years, this line has been popular among critics of the Insane Clown Posse, of which there are many. And it's often referenced to imply that ICP is dumb, basically. The implication is that ICP doesn't know how magnets work, or based on the song in which this line appears being called Miracles, that ICP believes that magnets are somehow supernatural, as in some mystical god or spirit or wizard is, pushing on the magnetic clasp of your girl's purse every time she closes her bag or something. This juggalophobic attitude is encapsulated by a mean-spirited and incredibly annoying video entitled Debunking Insane Clown Posse's Miracles by Andrew Wagenheim, which is visible on YouTube still as of the date of this recording. In this video, Wagenheim spends most of the 49-minute runtime giving extremely cursory level explanations for the various natural phenomena ICP describes in their song Miracles, discussing, for example, the reason why the sky is blue, the mechanisms by which mountains and other geographic features form, the reproductive mechanism of trees, the hydrodynamics of river flow, etc. The remainder of the 49-minute runtime is dedicated to shilling the terrible pay-to-win mobile game Raid Shadow Legends, so I imagine that Wagenheim's intent in making this recording is most likely primarily greed rather than juggalophobia, although I don't, really know because I'm not in his head, of course. There's plenty to dislike about this video. For example, Wagenheim fails to go into any meaningful depth when explaining any of the natural phenomena mentioned, as in you'd be better served probably just reading Wikipedia than listening to him. And instead of spending the time on in-depth discussions, which, I try to spend time on, he makes, or rather repeats yo mama jokes. And he's sure to include both of the major variants, the yo mama so fat type and the I banged yo mama type. So yeah, real original stuff going on here. The main problem with this debunking video, and the image of the debunker is certainly apropos here, is the assumption that because the song is entitled Miracles, every phenomena mentioned therein is something that ICP considers miraculous, as in no mundane or natural or scientific explanation could possibly exist. The reality is that music is very often metaphorical. The Insane Clown Posse is a rap duo, and rap especially derives from spoken word performance, from poetry. That's why live music is called a performance. It's a form of acting. You wouldn't debunk Matt Damon for acting in The Martian and say, Mr. Damon, you didn't really grow those potatoes on Mars. Show me some Martian French fries, then I'll believe. I mean, a music performance is a performance in the same way that a theatrical or cinematic performance is. I wonder if Wagenheim is going to debunk Shakespeare next. I mean, it wouldn't be hard to do. Let's take a look at Sonnet 18. Shall I compare thee to a summer's day? Thou art more lovely and more temperate. Rough winds do shake the darling buds of May, and summer's lease hath all too short a date. Sometime too hot the eye of heaven shines, and often is his gold complexion dimmed, and every fair from fair sometime declines, by chance or nature's changing course untrimmed. But thy essential summer shall not fade, nor lose possession of that fair thou owest. Nor shall death brag thou wanderest in his shade, when in eternal lines to time thou growest. So long as men can breathe or eyes can see, So long lives this, and this gives life to thee. Beautiful, beautiful. But did you catch that? Shakespeare said, "Shall I compare thee to a summer's day? Thou art more lovely and more temperate." Now, temperate simply refers to temperatures that humans find generally comfortable, as in temperatures that are not too hot and not too cold, a nice room temperature, you might say. Mumbai, aka Bombay, in the summer is not temperate, it's too hot. Moscow in the winter, and it's about to be winter here, is not temperate, it's too cold. Temperate is a temperature somewhere in between. There's no single absolute most temperate or most comfortable temperature for humans, which is obvious to anyone who has ever had a disagreement over a thermostat. Thermal comfort is going to depend on humidity, on the type of clothing worn, on the amount of physical activity done, and this is why surgeons love keeping operating rooms so damn cold, because, they're working, doing physical activity there. It'll depend on airflow, on the presence or absence of radiant heat from sunlight or incandescent lighting, etc. And this is why a room could be uncomfortably warm for someone who is dry and heavily dressed, but uncomfortably cold for someone who just stepped out of the shower. The general finding is that most people performing most types of physical and mental labor dressed in most types of clothing are most comfortable between 18 and 24 Celsius, or from around 64 to 75 degrees Fahrenheit, and my preference is certainly within that range. Yet here we have Shakespeare. He's going around telling us that his sweetheart is more temperate than a summer's day. Typical human body temperature is around 37 degrees Celsius or 98.6 Fahrenheit. But your sweetheart, of course, ideally she will be ovulating, ideally she'll be fertile. This is a sonnet, it's a fantasy after all. And while we're dreaming, we might as well dream big. And that will push her body temperature higher by perhaps 0.4 of a degree to 37.4 Celsius or 99.3 Fahrenheit. This is not a temperate level. An ambient temperature that high, while it's perfectly safe provided you have, plenty of water to drink, will be uncomfortably warm to essentially all people under essentially all circumstances. The human body necessarily generates heat as a byproduct of vital metabolic processes, and that heat needs to be dissipated to the environment in order to prevent internal temperatures from exceeding safe levels and denaturing your proteins and so on and so forth. If the environment reaches body temperature or above, then you're going to have a problem, and that is because of
the second law of thermodynamics. Heat cannot of itself pass from one body to a hotter body.
Heat cannot of itself pass from one body to a hotter body.
Heat won't pass from a cooler to a hotter.
Heat won't pass from a cooler to a hotter.
You can try it if you like, but you'd far better not.
You can try it if you like, but you're far better not.
Cause the cold in the cooler will get hotter as a ruler.
Cause the cold in the cooler will get hotter as a ruler.
Because the hotter body's heat will pass to the cooler.
Cause the hotter body's heat will pass to the cooler.
That's right, the second law of thermodynamics strikes again, beautifully explained by Mr. Michael Flanders and Mr. Donald Swan. If the ambient temperature really was, the temperature of Shakespeare's beloved, heat would no longer spontaneously conduct from his body to the outside environment, meaning that he'd start, sweating profusely, with the evaporation of the sweat serving as a sort of, active measure to keep his temperature within range. And this is not, generally speaking, something that most people find comfortable. Furthermore, Shakespeare grew up in Stratford-upon-Avon, where summer temperatures in July, that's the hottest month, typically reached a daily high of 22.2 degrees Celsius, that's 72 Fahrenheit. This is data I found based on recordings that started in the 1950s, but of course, Shakespeare was a young man in the 1500s when he wrote this sonnet, and temperatures were meaningfully lower back then as the Industrial Revolution and consequent global warming hadn't yet occurred. So we might surmise that a warm summer's day in July in Stratford-upon-Avon in the 1500s would measure around 20.5 degrees Celsius or 68.9 Fahrenheit, which incidentally is right around the middle of the comfortable, that is, temperate or preferred range in modern literature. So that's it, boys, we got him. We've debunked William Shakespeare. He said that his girl was more temperate than a summer's day. Wrong! How will he ever recover from this roast? Like, we've charred the bard, boys. Do you see my point? Do you see how nonsensical this is? It's just as nonsensical to try to debunk ICP's miracles. Shakespeare has every right to speak in metaphors, and so too does the insane clown posse. I personally prefer the works of Shakespeare, but they are both, after a fashion, poets. It's because of this sort of malarkey that juggalos can become quite, defensive whenever anyone repeats the fucking magnets, how do they work line, or even really brings up magnets in the context of ICP. It's understandable because they've long been subjected to what I think is, generally unfair and kind of pointless criticism when this line is taken out of context. The context being that this is a metaphor which portrays a sort of wonder and appreciation of the natural world rather than a literal claim that magnets are magical or supernatural or somehow miraculous. I've reproduced the meme for you here. It was quicker for me to reproduce it than to look for the old file. And it's also probably in higher resolution, I think, here than when I originally made it. I'm comfortable sharing it because I imagine that juggalos have, calmed down a bit after all these years. They have bigger fish to fry than me, than yours truly, especially now that YouTube has changed their search algorithm so that searches for ICP, which previously returned almost entirely insane clown posse related content, are now filled to the brim with cryptocurrency shitcoin nonsense. There's, of course, a shitcoin called ICP. And this is probably a much bigger, slap in the face to juggalos than any meme I could make. I'm also comfortable sharing this because I'm no longer afraid of my own death. I will note that the most frightening threat that I got, this was the one that was sent to me via email that I'll talk about, and it had quite a bit of information about me, including where I had studied, where I was working. They also attached a photograph of me to show that, the sender knew what I looked like. This email was actually about 8 months old when I read it. It was sent to my university alumni account, which I didn't check as frequently as my work email account. And also I had set up this kind of, system of folders and automatic filters based upon sender addresses and keywords, the exact sort of thing that I would do. And this email ended up kind of slipping between the cracks a bit, and it got directed into a folder that was intended for my alma mater's endless begging for donations messages, probably because the sender had included the name of my university in order to demonstrate that he knew a lot about me and, perhaps where to look for me. And I didn't check that folder very often, so by the time I actually read the threatening message, it was just a few days shy of 8 months old. So I suppose, I thought to myself, well, if this juggalo was, really going to kill me, I suppose he would have done it by now. Hence, the death threat was, in a sense, expired. Do death threats expire? I mean, I doubt that the statute of limitations would run that quickly. It's a felony, of course, to threaten someone like this. And for all I know, the statute of limitations still may not be expired, though I never reported this to the police and I don't really intend to. I don't actually have much of a concern about being murdered by a juggalo over a meme, and in any case, I'm well over it and I'm at peace with my own mortality. I'll also note that this sort of behavior that I experienced shouldn't be taken as a reflection on all juggalos. I mean, ICP has sold, something like 7 million copies of its various records, and the thing is, if, millions and millions of people listen to your music, some of your listeners are bound to be jackasses, unfortunately. That's just the law of large numbers. I'm also sure that if Joseph Bruce or Joseph Utzler ever knew about what was happening, they would have told, whoever was sending these threats to me to knock it off. But again, if you're a rock star, it's not like you have the time to intervene on every occasion when one of your fans gets mad about a meme someone made. So I've closed this chapter. Lord, forgive me my trespasses as I forgive those whomst have trespassed against me. I would say as well about chemistry, a lot of the content that you'll see, if you look in occupation media, like on YouTube or similar, and you look up chemistry, a lot of the content you'll see initially or at the top of the search results will be about preparing drugs or preparing explosives. And that's as a result of people essentially attention whoring for, likes or for ad revenue or for sponsor revenue or whatnot. And it's somewhat the same situation if you look outside the occupation media. If you look in more independent media and you search for chemistry, you'll still find a lot of information about making explosives, although it's probably for a bit of a different reason. that they're providing that a bit more of an educational reason. I might say I won't speak too much about that, but still, you see a lot of content about chemistry really being focused towards that. And I think, that while energetic compounds are an important field of chemistry, certainly there are many, aspects and avenues of chemistry that don't involve, blowing anything up or setting anything on fire or making any, psychoactive compounds. And if you really study chemistry deeply, you'll start to see those connections everywhere, and you can see that you don't need to kind of use that sensationalism as a crutch in order to create something that's, interesting for yourself and hopefully for others as well. And that's what I aim to do here in part with my investigations of photochemistry. Now it's time to make our citrate-based cyanotype sensitizer. I've saved my ferric ammonium citrate right here from the magnetochemistry boat experiment, and I'm also going to extract all that I can from this filter paper as well, so we can use hopefully the full amount. That's 12.984 grams, a 61.37% yield relative to our expected or ideal 21.1576 grams, with most of the loss coming from my terrible filtration and recrystallization, as well as loss due to the gustatory assay. Divided by the molecular weight of 520.21, that's 0.024959 moles. This is the number of ferrous ions we would obtain theoretically if every molecule of our ferric ammonium citrate photoreacted. Now, we know that we need a 4:3 ratio of ferric to ferrous ions to form Prussian blue, so we need 4/3 as many moles, or 0.033279 moles, of potassium ferrocyanide as our ferric ion source. Potassium ferrocyanide has a molecular weight of 329.245 grams per mole, so we'll need 10.9567 grams of it to match our ferric ammonium citrate. I'm going to put each of these solutes somewhat arbitrarily into 100 milliliters of water, and then we'll just mix them together. There should be no reaction, at least in theory. Some Prussian blue will form if the ferric ammonium citrate has undergone photoredox due to the lighting I've been recording this under, so likely we will see at least some precipitation, but it will hopefully be relatively minor. Nigel Braun noted on June 10th, 2018, that when mixing these solutions, he noticed what he called an emulsion, ostensibly little droplets of one solution getting suspended or entrained in another. I somewhat doubt there's actually an emulsion being produced here, in large part because potassium ferrocyanide and ferric ammonium citrate are both extremely water-soluble, and I don't think that you could end up with two immiscible aqueous phases. And sure, unfortunately, as I've seen, you can add so much ferric ammonium citrate to water that it becomes immiscible with something like isopropanol, but I really doubt there's any way to make water immiscible with itself. I think he's more likely seeing a suspension of some sort, a colloid, but I'm not sure, so I do want to mix these dropwise and see if I see the same thing. Whether I do or not, I probably still won't discover anything meaningful, but it's worth at least seeing if I can reproduce this. We're going for 10.9567 grams. 10.965 grams, that's certainly more than close enough. That should do it. As for our ferric ammonium citrate, this is going to be a bit messier of a process. First, I'll add what I have left over from the magnetochemistry boat experiment. Try to wash all this out. And I'll add in the other crusty filter paper bits, which have ferric ammonium citrate caked onto them. But this stuff is very water soluble, so as I add some water, I should be able to dissolve most of it and then just pull out the hopefully relatively clean filter paper, or at least hopefully not too much will be left in the filter paper. Well, it looks fairly good, but let this, I suppose, be a reminder to you that if you're dealing with a substance that's so polar that it's almost impossible to dry, it just really wants to stay in aqueous solution, you should probably just leave it in aqueous solution if you can tolerate that. And for the cyanotype process, it certainly can be tolerated. Here you can see I set up my addition apparatus. On the top we have ferric ammonium citrate in the water. And at the bottom with a nice white background, we have our potassium ferrocyanide. I just put it in the bottom flask because it's lighter generally in color, so I think it'll be easier to see if there's any colloid or suspension or whatever that forms as we perform the addition, but I'll bring the camera in even closer for that. We can see the formation of a bit of Prussian blue, which indicates that there is some damage effectively to our ferric ammonium citrate, that some of it has converted to the ferrous ion, although hopefully it won't be too much. We can now run things, I think, a bit faster. Our cyanotype sensitizer solution is now prepared. We did lose a bit of it to reaction to form a Prussian blue, which isn't too surprising as I prepared this under bright studio lighting. But certainly the majority of it hasn't reacted because I don't see any Prussian blue, clumping up in the bottom. And so I'll coat this on some paper and then we'll go out and make some cyanotypes with it. These absolutely beautiful flowers look like a good candidate for a photogrammetry. I have my equipment here. And if you can hear that sound in the background, it's a lovely sound, not great for recording, but that is the sound, of course, of running water, which means that we have a water source nearby that we can use for development. As you can see here, I've quickly set up my cyanotype frame. And once this is nicely printed, which I expect will take probably around 10-15 minutes in this light, we should be ready to go ahead and develop it in the fountain. There's a stereotype, of course, that Russia is always cold and snowy, and although there's certainly that aspect to it, which has its own charm, it can also be absolutely lovely in the summers. There's a definite blue color developing. And just incredibly convenient that we're so close to running water. Probably 50... less than 100, maybe 50, 80 meters away, and we'll be able to develop and fix this. They were sadly changing the light bulbs up there, so I'm not able to see the fountain too well. But if I step out a bit, it'll be quite visible. There we go. Now we're ready to remove the clips, and we should see a cyanotype image. The shadow. What? Water here looks clean enough. It's a bit contaminated by some ducks, but we should be able to wash this and get a good image out of it. There we go. Look at that. Beautiful. Beautiful. This is also the somewhat shady side. Look at these as well. Oh, looks like there's a bug of some sort landing on one. Absolutely gorgeous. They just have these kind of fractal flowers, and it's like, you have a bunch of flowers, and each bunch of flowers has a bunch of flowers, and each bunch of flowers itself has a bunch of flowers. Just gorgeous. Another one I think will be lovely. See how that flattens. Here you can see a pair of lovely cyanotypes that I made using Herschel's formula, the citrate process. This cyanotype I made in Izmailskom Parkya. I developed and fixed it actually in a river, though I didn't record that. The river bank was quite steep, and I was rather formally dressed and not too eager to fall into the muddy river. So I didn't risk, trying to wash the print with one hand while holding my camera with another, while kind of perched on the riverbank. I wanted to have one hand free to support myself. Then there's this cyanotype, which is of a still living plant of some sort, which was not meaningfully damaged by my placing it in a frame for a few minutes, I think. It's late September in Moscow in any case, and the snow will come soon, so all these plants will be dead shortly in any case. And I did ask one of the guards at VDNH if I could momentarily sandwich one of the flowers growing in a garden there in a frame, so long as I didn't pick it, and he told me that this was fine. You can also hear a bit of chatter in the background as I took the cyanotype paper out of the frame. When the end of the exposure was approaching, I kind of kept my eyes peeled for a large group of ideally large individuals, like, извините, вы можете делиться со мной вашей тень, просто стойте там 30 секунд, чтобы здесь было темнее. Can you stand there for 30 seconds? Can you share with me for a moment your shadow? Just to shade the cyanotype frame. And they weren't in a rush and more than happy to provide some shade when I removed this from the frame and then, put it in my relatively light type box and ran off into the distance into the fountain to develop it. And you can hear them chattering a bit about this in the background. This is, I would say, one of the biggest advantages of making cyanotypes in densely trafficked areas. If you need shade for when you're setting things up or, disassembling things or making some adjustment to protect your photosensitive paper from direct sunlight falling upon it, there are generally plenty of people around who are happy to oblige. The disadvantage, I would say, to cyanotyping in densely trafficked areas is that you really ought not to pick plants there. So if you're planning to pick live plants for your cyanotype, I certainly wouldn't do that, in the center of a public park or something like that, especially on a sunny day on a weekend when there are a lot of people about. The one exception to this rule about, not gratuitously harvesting plants is what Russians call krapiva, and I actually have some of it right here. Krapiva is actually two species. The first is Krapiva duodomnaya, or dioecious krapiva, which is Urtica dioica, and each plant is entirely male or female. These are perennials, and somehow in Moscow they overwinter even under, meter after meter of snow. I don't know how they do it, but they do manage to do it. The second is Krapiva žgučaja, or stinging krapiva, which is Urtica urens, and it has a mixture of male and female flowers on the same plant, and it's annual only. Russians call both of these species krapiva, generally speaking, unless you're speaking to a botanist, and they very much dislike these plants. Like if a Russian sees one of these species, he will feel an urge to pick up a stick and just, instantly start beating this plant, even if it isn't bothering him at all. Of course, if a plant is bothering you, you're, clearing a field, or you're planting an orchard, or something like that, and some unwanted plant is in your way, then you remove it. If a plant is being grazed on by your livestock and, poisoning them, making them sick, or it's, sending its roots into the foundation of your house and, breaking the foundation, or if it's presenting a fire hazard or something, you remove it, you clear that plant, obviously. But I'm not talking about these cases. What I mean is that Russians will just, attack krapiva without any discernible reason. It is true that both of these species do sting a bit, but to be honest, neither of these species is particularly dangerous. There are far more toxic plants about. And in fact, this krapiva specifically develops these little, stinging trichomes that you can see if you were to look at it close up in response to being damaged. The plant doesn't want to waste energy on self-defense unless it's truly necessary. And so plants that haven't been disturbed by humans or by, some kind of animals, chewing upon them or something, will usually not sting at all, or they'll, hardly sting at all, and they can be handled easily. These are the sort that you find growing in forests where they haven't been disturbed. But if you see a krapiva that looks like it's had Russians beating on it with a stick, or if you just suspect that it might have been beaten by a Russian with a stick because it's in an area that has a lot of foot traffic, you really should be careful handling it, because those, beatings will have caused it to produce many stinging trichomes in, self-defense against this attack. But because Russians dislike krapivu, you can collect it in any kind of reasonable amount for your cyanotypes, even from very densely, trafficked public places. And no one's going to bother you about this. I wouldn't, show up with a scythe and start, mowing down hectare after hectare of this stuff on land that you don't own, obviously. But even in that sort of situation, the Russians would probably be more concerned that you're walking around with a scythe like the Grim Reaper than that you're, going around and stealing all of their krapiva. Got a bit of a sting there from the stem, but not too bad. The sample that I have here is Urtica dioica, or Krapiva duodomnaya. So this is the dioecious crapива. This plant is either male or female entirely, although I don't personally know which. And if you harvest plants like this from a forest where they're undisturbed, you can handle them, without too much issue. I wouldn't recommend diving face first into a pile of this stuff, of course, but typical gentle handling isn't going to be an issue. So if you're kind to crapива, it will be kind to you. I didn't manage to get this from a forest, so it does sting, a little bit. But it was growing near a Pamiatic, like a memorial to Pamiatic Yuri Gagarin, a memorial to Yuri Gagarin, and so probably fewer people had hit it with sticks because they would be afraid of, accidentally hitting the memorial with a stick, which would be disrespectful. And so that means that it's not been as abused as most crapива, and so it's, kind of intermediate in its tendency to sting. It's now time to jump ahead in time from the citrate-based cyanotype process to the oxalate-based process, but because my rendering tests are showing that this recording is approaching 256 gigabytes even when highly compressed, and that, is an upload size limit for many platforms, so much for Moore's Law, I'll be covering the oxalate process as a part 2 of this cyanotype primer. This is the first video recording I've made of myself for general publication, and overall I've had an excellent time. A labor of love, not always easy, and certainly with moments of frustration, but I think worthwhile. There are many errors in this recording, footage that is out of focus, problems with audio quality especially, and surely there are technical mistakes that I've made that I'm not yet aware of, or else I would have corrected them, but I will discover them a millisecond after I upload this, and then I'll kick myself over them. But that said, I seek to learn from my mistakes and to refrain from making perfection the enemy of progress. Really, the audio quality has been for me the biggest issue. It's 1 part in 10,000 about of the data stream when you think about the relative shares of bitrate that are taken up by audio and video, but it's been well over half of all of my headaches, I can assure you. One issue is that my recording area, for whatever reason, has very high levels of electromagnetic noise. I found this to be the case in Russia in general. There is a lot of electromagnetic noise, here for some reason. EM noise doesn't usually cause too much trouble for regular people. I mean, if you're operating some radio telescope and you're trying to pick up alien transmissions from the Andromeda galaxy or whatever, and you get all excited because you think you've, contacted the aliens, you heard some great signal, and then you discover that it's actually signal coming from someone microwaving a burrito down the street. I mean, that's different, but most people don't really encounter these sorts of problems with radio frequency noise on a regular basis. In fact, when living in the US, I only had trouble with it on a single occasion involving a VGA radio signal from a computer into a monitor where my GPUs would cause quite a bit of noise in the signal and some, tearing and, spotting, or it looked like snow or frost in the video. I was running a pair of 7990s in Crossfire, where each of these 7990s is actually a pair of 7970 chips, which is linked, by Crossfire internally. You can see the 2 chips here. So you end up basically with 3 Crossfire links bridging 4 7970 type chips, which is called Quadfire, technically, because you have ultimately 4 chips that are each, 7970 type. You can see 2 here, 2 here. When I ran this, we just called it the Red Wedding configuration. This was back in 2013 when Game of Thrones was very popular, and although I never really watched it, I suppose the name was at least a bit appropriate. The 7970 I have here is finished by Power Color. I originally had 2 by Power Color, and the GPU fans are blood red, and they were married by a Crossfire link, which is across these contacts here. So that's where the name comes from. I imagine. I don't really know. I didn't come up with this. I have the cards, here, of course, this is the Power Color card, and this is XFX. I actually originally had a pair by Power Color, but one of them caught fire when I put it under load. I remember seeing, flames were jetting out from these holes and kind of between the board here and the back plate. So I think this was a fire in the VRMs, the voltage regulator modules, and not, from the 7970 chips themselves. Fortunately, I had installed an emergency power shutoff system, a crowbar circuit, where you hit the button and then it, shorts everything, disconnects from power, pulls all of the rails down to ground so that any capacitors are discharged to completely de-energize everything, and it worked exactly like it was supposed to. I hit the switch and the fire went out almost instantly. It hadn't reached the point where it was self-sustaining without electrical heat, so that was certainly a good thing. I returned the card, RMA, Return Merchandise Authorization to PowerColor, but the thing is I was terribly worried that when they got it back and, started testing the card, if they connected it to power, it would immediately catch fire just like it had in my system. And I told the customer support people, over the phone and via email at PowerColor about this, and they assured me it would be fine. I wanted to warn them, but I was still worried. So I took a Post-it note and I plastered it over the high current ports, and I wrote something on it, in English, of course, to the effect of danger, do not connect to power, short circuit, fire hazard. And, after I had affixed that to the GPU body, I packaged it up in, bubble wrap, and I put it in a shipping box, and I put the return shipping label that I printed out that PowerColor had issued to me, and I started heading to the FedEx office to send it back. But on my way to the FedEx office, I started getting worried. I thought, what if the people testing it are a bunch of Mexicans in a warehouse in Los Angeles and their English is not so good? The shipping label was for some facility in South LA. I thought also, what if LA is just one stop on the journey and it gets back to China or something eventually? That's where most electronics are manufactured. And some Chinaman who doesn't speak English properly, he can't understand the warning label that I wrote. And what if he, plugs this defective card into a power supply for testing that has 1,000 amps available on the 12-volt rails and it starts a fire? I was driving to the FedEx Center in East Oakland. For some reason, these shipping hubs are always in the worst part of town. So I was already a bit nervous, and I started having these absolute waking nightmares of Los Angeles, of Shanghai in flames, firestorms engulfing city blocks, embers, floating over the skyscrapers, widows and orphan children running from the blaze, the stench of burned hair on the billowing smoke, all because I had returned this card without including multilingual warnings, to inform people about the fire hazard. And, imagining that the people testing or repairing it couldn't read the warning that I'd written in English. And in this absolute haze of paranoia, I started having vicarious flashbacks to the My Lai massacre in Vietnam, those black and white photographs that I had seen in history textbooks so long ago. And in this moment, in the car, I was fully convinced that returning this defective GPU with English-only warnings made me morally equivalent to some, war criminal who dumped napalm and Agent Orange on innocent civilians. So at a stoplight, I reached over into the front, passenger seat to my right where I had belted the package in, and I tore the return shipping label on the box to shreds. I was planning on returning home, of course, and adding foreign language warnings and then, repackaging it and sending it out. But I started to have thoughts, while I was driving of what if I'm killed in a car crash on the way home and someone sees this box and thinks, well, this box has a valid shipping label on it. We might as well take it to FedEx and send it on what would be its grim path. What if I was to become the Grim Reaper even in death? What a twisted legacy that would be. I drove home, with this without being killed in a traffic collision, obviously, and then I went about adding the warnings. I had an elderly Mexican neighbor on my floor at Lake Merritt in my apartment building, and I asked him to write a warning in Spanish in bold Sharpie on a Post-it note. And at work, I asked a colleague who spoke Mandarin fluently to write a warning about the fire hazard in Chinese. This was back in the days of Babelfish. Google Translate did exist, but it wasn't any good. Really, it wasn't much good until, I would say, late 2016 or early 2017, and this incident was in 2013. So I recruited men around me to write the warnings in languages that I personally couldn't speak. I did add my own warning in French, and I also drew, a flame, kind of a flame logo or image in Sharpie on another Post-it note as a visual warning, to anyone who wouldn't be able to read what we had written at this point in French, in English, in Chinese, and in Spanish. And I secured these notes, all over the GPU with clear packing tape. And then I printed out a new copy of the return shipping label, repackaged it, and I sent it to PowerColor without incident. I had asked PowerColor actually to send me a replacement, but they refunded me my money instead. It was $1,250, I think, which, seemed like a lot of money back then. And I took that money and just bought an XFX branded card, which, has worked fine and for all intents and purposes seems to be basically identical to the PowerColor packaged card. The red wedding configuration is notoriously dangerous, or at least, it was. No one would even think of running something like that today. You can actually see on the back plate of this card, which is the power color card, there are these, circular scrape marks in the label, which is basically just from the fans of the adjacent card, rubbing up against it. Normally a 7970, which is either of these two chips, takes up 2 PCIe slots, and a 7990 is already consolidating a pair of these into the same 2 slots. So really, when you're running the red wedding configuration, what you're doing is you're taking 4 7970s, which would consume 8 PCIe slots, and you're jamming them into just 4 slots. It's not just the power density, though, that is the problem in this case. It's also that the crossfire bridge between these, which is, a cable connecting here, has to be short just because the signal delay caused by the speed of light, limit, will cause the cards to desynchronize if the cable is, much longer than a few centimeters. And keeping it short means putting these dangerously close together, so you have a square cube loss situation. The heat generation goes up by volume, the third power, but the surface area, and hence the potential for heat dissipation, goes up only by the second power. And if you look at these, each of these 12-volt high current ports will pull 150 watts. That's a bit under 15 amps, call it 15. That means that on each card, you're pulling, about 30 amps here, plus these cards also pull 75 watts over the PCIe bus. We rounded up before, so we can round down and call that 5 amps. So each of these cards, even at base clocks, is pulling close to 35 amps, and you have, two of them right next to each other. You're pulling 60 to 70 amps, just at base clock in a space that's only this large, and that's quite a lot of current and quite a lot of power for something this size. Now add to that the fact that you're not running reference cards and you're clocking them higher, and you're overvolting them to keep them stable under synthetic load, and you are running a synthetic load. I mean, at the end of the day, you aren't just asking for trouble with the red wedding configuration. You're basically begging for trouble. So it's really my own fault, I think, that I got electromagnetic interference on VGA. I mean, why was I running VGA and not, DisplayPort, as you can see here, or, the DVI ports, or converting DisplayPort to HDMI and running a monitor on that? I mean, if you have a pair of 7990s, it's not as if you're lacking in video outputs. You could run, 10 monitors in 4K, 60 FPS all simultaneously off a pair of these. You can set up 10 monitors. That would be great for day trading. I mean, imagine how many charts you could look at simultaneously. And certainly with 10 monitors, you'll work 10 times as fast, so you'll lose money 10 times as quickly on your day trades. And that's really a big increase in efficiency that's accessible in that way. So in a situation like this, why use the VGA off the motherboard? Simple, I wasn't playing games. And it's best not to load a GPU with video output unnecessarily if you're using it for something else. It gets in the way, you see. I got EM interference with this setup, and the Lord knows I deserved it. That is, however, the only time I've had such problems with EM interference in America. Here, however, it's been a huge problem, especially in regards to the analog audio signal that's coming off my microphone here. Perhaps it's not really about Russia, and it's just more about living in a large city. Moscow is a city of some 18 million, at least by official counts, though as in American cities, there are many illegal immigrants, so a true count is probably closer to 20 or 21 million. I've never lived in such a large city before, and cities, I imagine, just have inherently higher levels of electromagnetic interference. There's just going to be more people around, there's going to be more power consumption, you're surrounded by more electrical transmission lines and transformers and switches and high-powered motors on trains and electric buses and people using microwave ovens and induction, stoves and Wi-Fi routers. You're surrounded by radio and television broadcast towers and air traffic control and, military radar and so on. My microphone takes power over USB-C, as you can, see here. And when I used a Samsung power brick, and this is, a real one, I got terrible, terrible noise from the mains power, from wall power at, 50 hertz, which is the frequency here. So I bought this fancy power brick, which has, the full 100-watt, latest USB-C power delivery, which of course I don't need, but, it's new, so I thought it would be good. And it was slightly better. I did try as well my Lenovo charger. This is a 65-watt charger, again, more than enough. for my laptop, and that was significantly better. Not, too much difference between these two, but this was a big step up. But still, there was quite a bit of noise. And so what I decided to do ultimately was to buy this USB power pack, and I simply charge it from mains power. And then I disconnect it from mains and, connect it to the microphone. And that's how I power the microphone. That's the only way I found of getting the noise to an acceptable level, is to air gap it using USB battery pack. And I know it's very silly to use battery power when there's, mains power available, but this is the only working solution I've been able to find currently. This recording and supporting materials will be made available for download at freeworldblues.com. I released this work into the public domain under the Creative Commons Zero license. You have an unlimited, permanent, and worldwide right to copy, modify, and distribute this material for any purpose without consent, payment, or attribution to the author.
Альтушка для скуфа, новая программа доступна уже на госуслугах, никакого обмана. Можно с государства слутать шуги спидовок даром. Это значит бесплатно. От алтушки до жулебинат Нарьян-Мара и до Кемерово. Альтушкам надоело драться за кавалеров. Давно бы за пузиком уже теплым пригрелись. Но есть одна проблема, их оффлайн не найти. И мне нужен дейтинг, онли, ГГВП и рейды. Только вот налоги все равно ложкам платить. А без госуслуг туда им никак не зайти. Тут они все и попадутся в сети к независимым леди. Альтушка для скуфа, новая программа доступна уже на госуслугах, никакого обмана. Можно с государства слутать шуги спидовок даром. Скажи возраст, вес, рейтинг World of Tanks.